Welcome to the very first lecture of Crash Course Electronics and PCB Design. Now, ironically, this lecture was a course recorded as the very last lecture of the actual lecture series. I had to do the entire class, all the lectures, before I could record the very first lecture to figure out what was going to be inside of the resources for the class itself. So this is kind of backwards. So at this point, it's at the end, and I've edited the entire course, and now I'm talking to you again. So it kind of feels weird. Anyway, inside of this lecture, the resources for this lecture, you're going to find a zip file and maybe a couple other things in the resources. The zip file is the most important thing. This is what's going to have the parts list, all the files that are used and referenced inside of the lectures, the book, and so forth. So let's take a look at all that. So right now, if you were to download the resources, you'll see there'll be a zip file. It's called Crash Course Electronics 61418, or maybe a slightly later date. So this date will change a little bit, but it'll be Crash Course Electronics and then a date.zip. If there's newer files, they'll be dated newer. That zip file, when you decompress it onto your computer, you're going to find a number of directories here. So read the README text always in case there's any last minute changes. But each one of these directories contains the information for the lectures. Say if we use a tool like Circuit Maker or Lab Center Proteus or Octave, MATLAB, and so forth, those files will be inside of these directories. So this is just easier and better than having hundreds of files all over the place and all kinds of resources for each one of the lectures. There's just too many lectures. So this is much better. You just get them all right here. And even though I may reference in a lecture, download the files for this lecture, what that means is just download this single zip file and everything is inside of here. So let's just take a quick look in here just to, since we're here and we've got a couple minutes. So the course obviously is about circuit design, electronics, electrical engineering, and printed circuit board design itself, PCB design using Circuit Maker and Proteus. And we're going to get into that way more in the next lecture. This is just real quick. I just want to show you where things are. And then the next lecture, we're going to kind of talk about what the course is about. But right now, let's just get this stuff on your hard drive. All right, so Circuit Maker inside of here. There's some projects in here, and this is where you would find those manufacturing files. Crash Course Electronics book. This is very, very important. So with the course, you get a copy of my book, which is called Design Your Own Video Game Console. It's also called The Black Art of Video Game Console Design, the hard copy version of it, which you can get on Amazon if you want. But I'm giving you a free copy for this class that you can use, read the whole book, it's 800 pages. We're going to be using it just for the electronics theory sections of it, all right? The video game console design comes later. Maybe someday I'll do a class on that. But right now you go in this directory and design game console and some version number, and then it's a PDF, all right? So that's what you're going to be looking at there. All right, Excel, there are some files in here that we do calculations with. That's where you would find those. Lab Center Proteus, here's all the project files for, mostly these are all simulations that we do during the course, all right? Miscellaneous images and charts, it's just that, some images and whatnot that you might want to use as reference. Octave, if you haven't heard of Octave, it's like MATLAB, which you've probably heard of. And MATLAB is Matrix Laboratory. It's a mathematics package, the biggest and the best in the world as far as I'm concerned, but it's very expensive. However, you can get a free evaluation copy, and then there's also a free open source version called Octave, which is very, very similar, and we're going to use Octave, and this has code in it. Right now there's only one program in here, but that's where you would find that. And then the parts list for the course. Now, I'm going to talk about this just a minute. So here's the parts list. It's a PDF file, all right? And let's go ahead and take a look at what that kind of looks like in 1 second. But first, the other file you'll find in the resources for this lecture is the master outline of the course. So this is very similar to what's on Udemy as far as the outline of what each one of the lectures are. But inside of this master outline, which you'll be able to download, not only do we have and let me zoom in here a little bit for you, not only do we have the explanation of what files are where and that kind of thing that we're talking about now. But we also have some other things like books to download or books to purchase, things of that nature. And then we talk about the parts list, how to find the parts list, which I'm going to show you in a second. And then each one of the sections of the course has the lecture, the description, the course title, and then what everything is about. So you can kind of read through this and you know, this is really easy to search through and scroll through and find everything. Additionally, inside of many of the lectures, I'll make a reference to a link or something like that on internet that we're browsing, and they're very hard to see as we're doing that. So I'll copy those links in here. So this is your resource. So you definitely want to go through this, and it's called Crash Course Electronics Master Outline, and it has a version number. You want to download this and go through this and just have this open as you're working. So it's not too big. I think it's like 30 pages maybe. Let me scroll down here. And this has kind of, yeah, so it's what, 39, 40 pages. So definitely have this open and go through this to kind of see what's going on. All right, so that's kind of the master outline of the course, right? Now there's also the parts list. Let's talk about that real quick. So the parts list PDF, and what this is kind of an overview of all the things that are going to be used, almost all the things that are going to be used as I build experiments on the bench in real time in front of you. Now, it's really important to realize that I'm going to add a lot to this list, because this list is kind of a general list of things that you should have if you want to do the experiments along with me, but then also things you should just buy to have if you're going to play with electronics and experiment. So, you know, we may only use, in this case, like a FET. Maybe we're only going to use the 2N7000 FET or something else, or the FDC606, but I'm going to add more here so that you have some options, just some suggestions that I didn't have time to describe during whichever lecture, all right? So this is kind of a big list. It's a shopping list of all kinds of things that you might want to get as you build electronics and as you follow the course, all right? So it goes through everything and describes things, explains things. There's some really big searches. I probably could turn these into tiny URLs someplace, but you know, I just didn't do that. And these numbers next to each one of the components just means I would suggest you get 10 of them. When you're buying electronics, the electronics are pretty cheap, but the shipping is not. So you're shipping like fractions of an ounce, and the shipping is $20. You might as well get a lot of parts because you're going to need them for different builds and different projects that you're going to make. So you might as well order enough of them. All right. So what I suggest you do is just peruse through this. I know you want to get it started on the lectures, so you can kind of jump in to the next lecture, but just kind of peruse through this, kind of scroll through it, take a look, and then when we're building a project in, say, one of the lectures, you can kind of go back to this and read more and look more and see what exactly I was talking about in that lecture, right? But anyway, this is a big parts list, and then there's some commentary about purchasing things like oscilloscopes and logic analyzers and things like that that I didn't maybe do in the lecture that I put inside of this text here, all right? So again, this is not too long, it's 20 pages, 23 pages, all right? Now, again, you're going to see this almost immediately, but I'm just going to show it to you real quick. So the book that goes along with the course, like I said, it's a free copy for students, and here it is here. And you'll download that inside of the zip file where we looked at it. Design your own video game console, and then the hard copy version on Amazon is the Black Art of Video Game Console Design. All right, but the book has a very large section on electronics and electrical engineering, and all these chapters we are interested in, and we're going to use these as our basis for the course. Just as a reference, so I have something to talk about as I'm going through things, so that we don't have to reference someone else's book and have you purchase something. So you basically get a free book with the class. All right, so that's it. Now another thing I may mention in a couple lectures you know, from here is that we installed the software already. We didn't install the software. We're not going to do it right now. I changed my mind. So the two programs, well, we're going to be using a number of programs. Like I said, we're going to use Circuit Maker because that's what the class is about, building printed circuit boards with Circuit Maker. But we're going to do that way down the line. First, you got to learn electronics, right? Also, we're going to learn, we're going to use Proteus, Lab Center, the name of the company that makes Proteus, and that's another CAD program for schematic design and PCB layout, but it's not free like Circuit Maker is. But the evaluation version is free, and we can just use it for simulation. And so we're going to use that for simulation, and that's the Proteus part of the course. But I decided the installation was fairly complicated and I want to do it right when we use the tools so you can kind of see how that goes, right? And we're going to install those tools and other tools and play with MATLAB and different things. So we'll do those installations kind of just in time when we do the lecture on it. So don't worry if I made any comments, you know, from here to someplace else in another lecture and say we already installed it. You'll know when we install it because we're going to install it. All right, so that's it. So I'll meet you in the next lecture and we're going to actually talk about the course and kind of a general overview of what we're going to do in the course. All right, so I'll see you there. Bye-bye. All right, well, how are you doing? So welcome to section 2. So before we get started with the actual lectures, I just wanted to talk to you for a minute to let you kind of know what we're doing, how we're going to do it, and kind of the general flow that we're going to do. So the first thing is, you know, if you've watched a lot of online, you know, courses, you know, I know I have, a lot of times the courses are completely scripted. And if the course is scripted, it's basically someone's just reading to you from something that they either wrote or someone else wrote. So number one, this is not scripted. So I'm doing this completely on the fly. So of course we have our outline that we're going to follow and all that. But you know, since I'm not in a classroom with you, and normally if I were in a classroom, I would just kind of have my notes and I would just be teaching you just as we went. Now, we don't have, I don't have the interactivity with you, which normally I would adapt every lecture depending on who's in the class and the kind of questions that are being asked. So what I'm going to do is, since I've taught this material a lot of times to a lot of different people, I'm going to imagine, you know, kind of the questions that they ask, and so I'm going to kind of be your evangelist. So as we go through this, I'm not going to, you know, assume that you know something that you may not know, and so I'm going to, you know, try and really explain things really well to you, and I'll take a lot of, you know, detours for a minute. So I may go talk about this or talk about that, and then come back. All right, so that's number one. So. You know, imagine we're just in a classroom. It's going to be you and me, and we're just going to do this, and we're going to get through this, and we're going to have a lot of fun doing it. The second thing is you can see that I've got some text up here on the screen. So as I said in the first section when we kind of went through the parts that you're going to need and resources and whatnot, one of the things is I'm going to base my lectures, my kind of theoretical lectures, I'm going to base them on one of my books. So this way I don't have to be fumbling around with new notes and kind of making up stuff. I'm going to do something that I've already done that works well and kind of has the material that I have in it. So what we're going to do is, and you do not need this book at all, but we're going to be using my Black Art of Video Game Console design book kind of as the basis of our notes and what we're going to kind of go through. Now, there's a lot of material in electrical engineering, embedded engineering, countless volumes can be written about it. So there's a list that you should have seen in section 1 of, you know, books that I recommend you read. Some of them are very theoretical, college text kind of books, and you know, and those are great if you have the time to do it. So, you know, for example, here's, you know, an old favorite of mine. This is a circuit analysis book by Johnson & Johnson. Many universities use this book. And I think, yeah, this is like the 3rd edition. So this is a great book. And if you have the time, money, you can, you know, buy this, download it, whatever. All right. So, but that's college text kind of stuff. Now, even if you have a degree in electrical engineering, the book I'm going to show you next, which is also in section 1, is one of my favorite books, and it's called The Art of Electronics, and I don't have the cover anymore for this. It got destroyed, but The Art of Electronics, and they're actually up to a new edition. And this book is really, really good. And the reason why is it doesn't have a lot of math in it, but it goes from, you know, the beginning to the end of everything electronic. And so this is another great reference that I suggest you read. So I actually, no matter what you do in your lifetime, if you are interested in electronics, you have got to read The Art of Electronics. All right, and this is by Horowitz and Hill. So, and like I said, they're up to the third edition right now. So, and it just came out, I think, last year. So that's really cool. And I haven't even got it yet. I need to get it. All right. But we're going to use my book, and my book, Video Game Console Design, has nothing to do with what we're going to do, but the electronics section of it, the theory is really good, and we're going to use that, and that's what you're seeing up on the screen right now. So that's what we're going to do. So we're going to do lecture, we're going to do theory, and then the whole idea of this is for you to learn basic electronics. All right. And it's important that you learn really good fundamentals. All right. And now the majority of you are going to be coming from a software background. That's kind of one of the points of this is, for people who kind of have a background in programming, you want to learn about electronics. So, and just like in software, you want to have a really good understanding of a computer architecture. How does a computer work? How does a microprocessor work? How does a program work? And if you don't have that information, you tend to write programs that don't take advantage of the architecture, right? Or run efficiently or use up too much memory. And I think everybody can agree that software these days is really bloated, right? So same thing with electronics. I want you to have a really good foundation and to be able to go through this stuff so that you can always kind of go back to that foundation. All right, so that's going to be important. So we're going to take our time, and we're not going to dig super deep, but we're going to dig deep enough that you're going to kind of understand where these things are coming from, and you can always research more. All right, the other important thing is, since this is Crash Course Electronics, we are going to be doing a lot of hands-on stuff. So, reading about something and hearing about it is different than seeing it done. So once you see actual hands-on things, that's going to really help. And then, I suggest to you, you do the same thing. The more that you touch these things, the more that you play with them, the more that you get a feel for them, that's going to help you, because you really have no sense of how these things work. It's like if you've never done something, you don't know how much, like if you've never picked up a certain object, you can't really tell how much that thing weighs, right? So electronics is the same way. You have no frame of reference to know how small these things are, or how much power they use, or how expensive they are, or where you get them. So the more that you interact with these components and play with them, that's going to be a good thing. So we're going to do that. So we're going to do theory. We're going to go over to the bench over here, and we're going to like play with things, and we're going to build things, and we're going to continue building things as we go through the course. Now, another thing is, I'm going to jump all over the place. So one of the ways that I teach when I teach a class, or even when I write a book, is I like to kind of jump from subject to subject and kind of make connections between them. And that really helps, because as you're learning something, it's like you're learning something just in tunnel vision, like if you're learning calculus, right, or physics. And it's just like you're just learning this and learning this, but you can't relate it to anything, and you just forget it. Right? I mean, a lot of people go to school and they might get straight A's in advanced math or something, and then later in life, they can't do an algebraic problem because they never use it for anything. So we're going to try and relate this stuff to different things so that you remember it better and start to get a feel for it. So that's going to be really important. So you're going to see me doing that. So some things may be like, why is he doing this, or why is he showing me that, or whatever. I have my reasons. So I'm going to always do that kind of stuff to just kind of help you understand things and relate them. Okay, the other thing that this course is all about is we want to learn electronics. We want to learn how to build electronics, simple stuff, right? Simple stuff. This is a beginner course. But we also want to learn how to use a CAD tool to draw circuit boards. So we want to learn how to do schematic capture and lay out circuits, and so that we could actually send them someplace and have them manufactured, and we could solder the things together and make them work. And that is a lot of fun. So even if it's a simple circuit, a blinking LED, which maybe you don't know what an LED, well, I guess everybody knows what an LED is now because LED lighting. But just a blinking LED, just make a circuit that blinks, that you actually designed and made and manufactured, that is awesome. And then that's the stepping stone. That's like the hello world of electronics, blinking LEDs. So we're going to learn to do all this, and we're going to learn this CAD program, which of course is Circuit Maker. And we've already seen Circuit Maker before when we installed it in the previous section, but here it is here, and we're gonna talk about this, and we're gonna go through it slowly. Once we have enough basic electronics knowledge, we'll start working with that program and start kind of laying things out and playing with that. All right, let's see. So I think that's about it. So this is gonna be a lot of fun. We're gonna do this together. And I guarantee you, by the time that you're done with, with all these lectures and all this course, you are gonna, know a lot more than what you started with, and you're gonna figure out that, electronics and embedded engineering and all that is a lot of fun. And if you're a pure software guy, you know, then you're gonna think, wow, I mean, I can make things in the real world, and that's really cool. And then luckily, my background is both software and hardware, so I know kind of how you're thinking, and I'm going to kind of play to that and try and make analogies to help, understand kind of these, physical things and maybe how they relate in kind of the virtual world. All right. So anyway, so that's it. Let me shut up. And what I want you to do is go ahead and finish this video, finish this lecture, and I'm going to meet you in the next one. And we're going to start talking about this and going through this and getting it done. Oh, and one final thing. Uh, I looked at a lot of different courses, and some of them have very, very short lessons. And so I feel that, our lessons are going to be more like lectures that you would have in a normal college level course, and a normal lecture is about an hour. So I probably won't go an hour, but I might go 20 or 30 minutes. And I wanted to have enough length so we can kind of get into the material and not just kind of do something quick where it's just like we're in, we're out, and what do we even learn? So these are going to be longer lectures in general, so we can sit down, we kind of work on something and kind of talk about it, all right? And so that's what we're going to do. So we're going to have a little bit longer lectures than normal, and so that none of these little 1 minute, 2 minute, 3 minute things, they're going to be a little bit longer so we can get something done. All right, and that's going to be important. All right, so that's it. So I'll meet you in the next one. And here's here's electronics over here. Here's your brain. These things are going to come together. All right, so get ready for it. All right, bye bye. All right, so welcome back. So this is the next lecture in section 2, and we're going to start off with some theory here and kind of look at a few parts, and we'll see how it goes. All right, so let's begin with the whole idea of this theory section, and we're going to spend some time on this. We're going to spend a few lectures on it, quite a few lectures on it, is we want to learn fundamentals and definitions, units, things like that, so we all have a vocabulary that we can communicate with. All right, so that's important. One of the big problems with electronics is, like, a lot of times you kind of just, people learn how to hook something up, but they don't really understand what's going on, and so it's unscalable. So you kind of know how to hook up one circuit, but how do you make that into 2 or 4 or something else, or more power or less power? So it's important that you understand the fundamentals, and so that's what we're going to be doing. This is going to be the first lecture, and we're just going to start going through this material and learn everything we need to learn. All right, so let's start off. And so I was looking, for a good definition, and the definition that I have here of electronics, the word electronics, is not bad. So let's actually read this. So the word electronics is derived from the word electron, which is the subatomic particle that has negative charge. Thus, electronics is the study of electrons in action, more specifically their properties in electrical circuits. More fundamentally, though, electronics is based on electromagnetic wave theory, which is the study of electromagnetic fields and their respective properties. However, and this is really important, electronics has simplified the field theory into manageable models that can be used to create circuits that perform various functions. All right, so this is super, super important here, and I'm just going to kind of highlight this a little bit here. The idea of electronics is that we would never be able to do anything with electronics if we were to go all the way down to the underlying physics and use like Maxwell's equations and atomic theory. It would be incredibly complex. So what's been done with electronics is simplified models have been developed so that we can, under certain circumstances, make certain assumptions, and we can design things and use these parts in a way such that their performance or functionality or the amount of error incurred is tolerable so that we can get things done. All right, and that's what we want. So at the end of the day, we want to be able to use things with simplified models so that we can get work done, so we don't have to go and work with differential equations and Maxwell's equations and down at the atomic physics level. All right, so okay, so that's that. So let's keep that in mind. All right, so let's go and continue on here. All right, so when when talking about electronics, let's get rid of this stuff here. When talking about electronics, you're going to hear two different terms. You're going to hear analog electronics and you're going to hear digital electronics. All right, so let's try and differentiate what these two things are. All right, so analog electronics has to do with smoothly varying signals. So signals that can take on any value from, say, one point to another. All right, so from 0 to 10 volts, and we don't know what a volt is yet, but any value in between there, 0 to 10 volts, it could take on. So an analog system is continuous, and it can smoothly vary from kind of one value to another. All right, now you can look up an exact definition, but so the thing to remember is it's smooth, it's continuous, and we have all values. We work with all values in analog electronics. All right, so let's take a look here at some signals that are kind of analog-ish. All right, so so on this little chart right here, we've got some different signals. Now, typically when you see electrical signals, they'll be graphed as a function of time. So the horizontal axis is time, and the vertical axis is something else, typically voltage or current, could be other things, but in this case it's voltage. And we don't even know what voltage or current is yet, right? But for now it's a magnitude of something. So, you know, we all kind of know 12 volt, 6 volt, 5 volt, things like that. So it's a magnitude of something. All right, anyway, so if you look at all these waveforms here, so here's a square wave, goes up and down, it has a period, and it has a pattern, all right? Triangle wave, same thing, triangular, sawtooth wave, and then a sine wave here, all right? And then we go down a little bit more, and we have this audio wave, which is kind of all over the place, all right? And so all of these waves could represent, you know, analog signals, all right? But this top wave right here, a square wave, is kind of more digital in nature. So it's 0, then it almost instantaneously changes to 1 volt, and then it's 1 volt for a while, then it instantaneously changes to 0 volts, and so forth. All right, so this is kind of what you'd see in a digital system. But the thing to remember is that everything is analog. There's no such thing as a digital system, ultimately, right? A digital system is a model, all right, that is based on analog electronics, where we use the model in such a way that we look at kind of an extreme case. Things are on, things are off, and the changing from on to off happens so quickly we don't really pay attention to it. So we'll get into that in a second. But anyway, so analog systems is the basis of everything. All right, but again, analog electronics and analog design is fairly complicated, so we want to simplify that, and that's, you know, how digital electronics came about. All right, okay, so let's move on here a little bit. Let's see what other interesting things we have here. All right, so now when you're doing analog kind of design, very simply, let's just go back in time. Say it's 1950, 1940, 1960. There wasn't you know, any real digital electronics at this point, all right? So when you built electronic systems, you built them out of these simple building blocks, all right? And so there's more than what I have listed here, but these are kind of some of the major ones, all right? So we have resistors, they resist current flow and they drop voltages. Capacitors store electrical charge, all right? Inductors store transfer electromagnetic energy, and capacitors and inductors are kind of opposites. They go together. Diodes, here's our first semiconductor device, allows current to flow only in one direction. All right, and transistors uses amplifiers and switches. These are also semiconductor devices. And then also in transistors, we would have what are called FETs, field effect transistors. Those are kind of the two major players. And then we need power somehow, so we either have current sources or voltage sources, or we have, you know, electrical batteries, right, chemical batteries, right? And then we have to connect these things somehow, so we kind of have to have wires or conductors. So with these basic components right here, you can build a lot of things. And this is how things were built, like radios, power supplies, you name it. You can build them out of these kind of basic components, right? A few more, like I said, we don't have them all listed here. All right, so right now let's take a quick look at what some of these things look like, so you can kind of see. Everyone knows what a battery and a wire looks like, but let's take a look at some of these other components just to make sure we know what we're talking about, and see what these things look like a little bit, and we'll talk about a couple things. All right. Okay, so what we're going to do is we're going to start taking a look at things, and I'm going to kind of show them to you, and then we'll kind of zoom into them so you can kind of see. All right, so first, let's start off with resistors. All right, and resistors are pretty simple. So let's get a couple cool resistors here. Just grab a couple random things, and I'm going to show you some different stuff here. All right, and kind of that one's burnt. Okay. All right, so first thing is, so here's a little resistor. All right, so let's put this down here. So here's a resistor here. All right, let's maybe zoom in a little bit here for you. And right about there. Okay. All right, so there's a resistor. There's a resistor. Here's another one. This is a kind of a power resistor. You can see this one's got a little charring on it. That was heated up a little too much. Here's another resistor. All right, see it's getting larger. Again, this is a power resistor. And then here is another resistor, and this is a very large power resistor. Okay, so now let's kind of take a look at these a little bit closer. All right, so if you look here closely, you will see that the resistor itself has some colored lines on it. All right, and if we go ahead and look at these, so in this case right here, this is brown, black, yellow, and then gold. So these lines are used to determine what the value of the resistor are. So, and then this, there's what's called a color code, the resistor color code. So we're going to learn that right now. We don't need to worry about it, but that's how you read what that resistor is. Now, one thing is this resistor has leads, okay, and see these leads, you can bend them, right? You don't want to bend them too much. All right, if you keep bending that back and forth, that will break. All right, and these have leads because this is called a through-hole component. And the reason it's called through-hole component is because you put it inside of a circuit board, a solderless circuit board, or an actual circuit board, and put it through the holes. So, for example, this is a solderless breadboard, and this is something that we breadboard with, and we're going to be using this. So don't worry about it too much right now. But one thing is, we can put this in here and pop it in like that, and then there it is. And then electrically, these things are tied together in columns, and we can build circuits out of this by adding wires to it. All right, so that's why it's called through hole. Now, another reason also to kind of bring that point home is, let's take a look at, let me grab a circuit here. So here is a printed circuit board. All right, let me back out of this a little bit. So here's a printed circuit board, and just something that that I made for a project or a product. All right, and then you'll notice that there are holes in the board, and those holes are exactly for resistors and components to go into. So for example, if we're lucky, this will go right in here. All right, and so we pop that in there. So, and then we would turn it over, and then we would solder it on this side. Okay, so that's why it's called through hole. That's why it's called a through hole component. And every one of these components kind of has a footprint. This footprint right here is a radial footprint, right? And then you can also see here are some surface mount components, right? In a minute we'll take a look at those, all right? So that's why things are through hole. They go through the holes in the printed circuit board, all right? And some things go on the surface mount, all right? So let's keep looking. Okay, so now we got that resistor, and here's another one, and we'll kind of do a comparison here. So there's the first one we had, and that one's much bigger. The reason why they're bigger is the larger one can handle more wattage. All right, so this tiny one is a 1/4 watt, I believe, and this is probably a 1/2 watt resistor. All right, so that means that how much power it can dissipate. Again, we don't really know exactly what a watt is, but we're going to figure it out. All right, and then here's an even bigger one, power resistor, and you can see I even scorched it a little bit right there. So that one's been scorched. All right, and so there's a power resistor. All right, and getting even bigger, take a look here. Here's another one, even bigger power resistor. So these are going to go, you're going to see these in power supplies and things of that nature where you are generating a lot of current and you need resistors in there. All right, and again, we're not quite sure what resistors do. We're going to learn about it. All right, and here's another resistor, and this is another power resistor. And you can read, instead of reading a color code, this is 5 watt and it's 1 ohms. All right, so this is a 1 ohm resistor. All right, I believe this one is 1 ohm. All right, so again, sometimes you have to figure out how to read these things. So this is 5% tolerance. I believe it's 1 ohm, but it could be 10 ohms. Let's check it out. So what do we do? All right, so if we can't read these things and we are not sure about what's going on, then we're going to use a multimeter, and this is one of the pieces of equipment that you need. All right, so let's go take a look, and let's back out here. All right, so this is a multimeter. All right, let's back out a little bit more so you can see it a little bit. All right, so that's a multimeter, and one thing you're going to learn as you start doing electronics is you can never have too much equipment. All right, the more equipment, the better. So a multimeter is a device that can measure voltage, it can measure current, microamperes, milliamperes, amperes, and see this one's so smart, it's saying, hey, when you're in current mode, you need to put the probes in here. All right, it can measure, this one can measure frequency and temperature and sound. It can measure light. So this has a lot of different features. Now this one does not measure, I don't think yet. No, this one actually does. This one actually has a capacitance and it'll check diodes for you. So this is a really cool meter. It's a low-cost meter. In the world of meters, there's a company called Fluke that makes really good equipment, but it's very expensive. And now there's many manufacturers that are low cost that make things just as good. All right, so again, you're going to need a digital multimeter. We're going to talk about this, and like I said, you can just never have enough of these, right? I've got a lot of meters, and each one of them has different properties, and there's more. But, each one has different properties that I like, and sometimes I just need many meters to measure something. All right, so anyway, so let's go ahead and we're going to take a look at this meter right here, and we're going to use this. And then what we're going to do is we're going to measure our guy over here. We're going to measure our resistor. All right, so first what we're going to do is we're going to turn this on, ohms. All right, and that's what resistors are measured in ohms. All right, that's their impedance. And again, we're going to learn about that. All right, and meters have different scales, and so this is an auto scaling meter. So what's going to happen is you can see that it says auto up here, and it's going to try and scan the component at different value ranges until it kind of locks into the range, and then it'll drill down and figure out what the actual value is. All right, so let's just do a quick check here. So how we do this is we just basically take the probes, all right, and we put the probes over the component, and now we actually are impedance as well, but a human being's about 100 to 200 kiloohms, so as long as the resistor is much smaller, we won't notice that too much, or just try not to touch it too much. All right, so we touch it on there. All right, we touch both leads, and it's tracking, and it's figuring out, so it says 0.470 K, or 470 ohms. All right, so 0.47 K ohms or 470 ohms. Okay, so that's 470 ohms. Great. Now let's come over and we're going to get this big guy. All right, and we believe that this is 1 ohm, I believe, but it might be 10. So we're going to put it on the two leads there, and we're going to see what it does. And it looks like it's 1 ohm. All right, so that's correct. So it's 1 ohm, not 10. But again, if you don't know how to read these things, just get out your meter and check it. All right, so that's 1 ohm. All right, and you'll notice that it's not exactly accurate. So we've got all these decimal places here. So now we can kind of change the range now that we know what we're dealing with. And now I'm going to put it into just ohms. And now it's getting more accurate here. So it says it's 1.1 ohms. All right, now these devices to measure this, it runs a current through it, and then it senses the voltage through the same cables. And this is a little bit inaccurate. So when you start getting down to very small values, it's harder to measure them. So you have better and better meters that cost more and more money. All right, and there's different ways to do that, but we'll talk about that later. We don't really care about it right now. Okay, so we turn our meter off. All right, so let's keep going. So the next component that we want to talk about is, let's see, let's talk about capacitors and take a look at some of those. All right, so let's come back down in here. All right. Okay, so let's bring out some capacitors and see what we got here. So first, there are many, many different kinds of capacitors, and there are some that you've probably seen quite a bit of, right? And I'm going to show you a lot of things, a lot of way that I do things. Okay, so you see I've got this little bin here. Electronic components are really, really small, and you will lose them. So see here, this is like my 22 picofarad, 47 picofarad, 100 picofarad, all right? And these are ceramic capacitors. And then here's some other ones. And so there's different ways of keeping them, but these things are small and you will lose them. All right, so different kinds. These are all ceramic capacitors right here. All right, so let's take a closer look at one of these. All right, so I'm going to let me grab a little blue one, and I'll grab a little orange one. All right, and let's go over to the zoomed camera. Let's take a look. Okay, so in this case, so this is a ceramic capacitor. And you can see it says 101. All right. So this is the value of it, and I'll show you how to read these later. But this is usually measured in picofarads, and so it's 1, 0, and then the last digit is a multiplier. But again, sometimes these things have different kinds of encoding, so you gotta make sure you're reading it right, and different vendors do different things, and you can always get your meter out and check it. So this is a ceramic capacitor, and it's not polarized, so it can go in a circuit either way, and it has certain properties. Ceramic capacitors are probably the most widely used now. Before it used to be electrolytics, which I'll show you in a second. And here's another ceramic capacitor. And again, this one, let's see if we can get on there. Yeah. So that one again is that's the same value. That's the same value as the one we were just looking at, the orange one. And yeah, 101. Yeah. But you can see it's a little bit smaller. So there's a couple reasons for that. So one is the materials that it's made out of might be slightly different, and then also the voltage that it can withstand may be different. So a large capacitor typically will be able to withstand a larger voltage than the smaller capacitor. And we're going to learn about capacitors and what that even means, all right? So, okay, so we got those two right there. Okay, let's keep going and see what else cool stuff we can find here. All right, now back here, we've got all these capacitors, and it's kind of a little grab bag. So as I'm building things and as you're building things, you got to figure out different ways to hold things. So kind of here I put my electrolytic capacitors. So electrolytic capacitors, let's take a look at some of these. So let's just get some colorful ones here. And electronics is also fun because it's a lot of color. All right, so here are some. So let's take a look at these and see what we kind of got here. All right, so let's bring them over. And so the first thing that we notice is the leads are coming out from the bottom here, all right? And so one thing is these leads are bent right now, and I don't like bent leads. So one thing I want you to get comfortable with is kind of using tools and messing with things and kind of fixing things up. So see, I just got these little diagonal pliers, and I'm just kind of straightening that out. See that? Now I'm happy. All right, so that's pretty. All right, so let's take a look at this. So this is an electrolytic capacitor. And so a couple things. First, you see this electrolytic means it's polarized. So it has a plus and a minus, and it works in that direction. If you don't put it in that direction in your circuit, it'll explode or not function or do bad things. All right, next, it has this negative here. That means this is the negative side, and the other side must be the positive side. All right, now you'll see a couple other things here. It's got a value 150 microfarads. Again, we don't really know much about capacitors yet, but we're going to learn they're measured in farads, and they're usually measured in micro because a farad is huge. All right, 150 microfarads, and then usually right next to it is the voltage that it can withstand, and this one can withstand 10 volts, so it's a 10 volts, 150 microfarad, and then the other writing is the manufacturer on there. All right, now this is called a radial capacitor, and the reason why it's radial is because the leads are out here radially. All right, and so if we have a circuit board like this one, put this one in here, and we can see where this guy could go in a place like that, and I just put it in wrong, right? So a capacitor goes there, but you can see there's a plus there. I actually put a plus to remind myself that's the plus side, so the other side's minus. So when I actually manufacture or assemble this, I would put that in there like that, and then I would solder it together like that. Okay, so that's radial. All right. Now let's take a couple other ones here. So here is another one, and this one is 35 volt, 47 microfarad. All right. So this one's a much higher voltage, right? 35 volts it can withstand, and it's 47 microfarad. And the other one we had, no, excuse me. This one, yeah, this one was 10 volts. This is 150 microfarad. So they're roughly the same size, but they swap capacitance for voltage in those two. All right, so let's take a look at another one, kind of a bigger one, and take a look at this one right here. So this one's interesting. So this is 250 volts. This is a capacitor that might be used in a high voltage circuit, right? 250 volts is very high voltage. So this might be in a power supply, AC/DC power supply, and where you need this high voltage tolerance. And this is 47 microfarads, all right? Again, it's radial, all right? And let's see. Here's another kind of littler one, little tiny one. And again, this one is 100 volts, and but only 1 microfarad. All right. And again, these leads, they kind of get wound up and messed up. Just kind of bend them back in place. All right. So there are some of those capacitors right there. Now let's take a look. There's another kind of capacitor, and there's many kinds of capacitors, countless capacitors. These are called tantalum capacitors. All right. So let me show you this. These are tantalum capacitors, and tantalum capacitors are also polarized, and you can see the little pluses. So if you look here carefully, you can see, get a little tip here, right there is the plus, the other side is the minus, and you can see there's 35 on here. These are 35 volts, right? And then you can see the value is 106. 105, 105. These are actually 1 microfarad. When you do the math and do the little encoding, it's 1 microfarad. All right, but I'll show you how to do that. So these are dipped in resin, and these are really good in power supplies. So you're going to see these in a lot of power supplies on the inputs and outputs, and they have good properties for that. But these have kind of been overran by ceramic capacitors as well. Because they're low cost. All right. So anyway, so those are tantalum. And now, so what is this? So this is a tape, and this is kind of how these things come. So again, these are through hole, and so see, these are cut. So I cut these off. So now, if this was a manufacturer, a robot, this tape would be loaded into a machine, and it's usually on a big reel. And then the machine sits and comes across and it grabs these and cuts them, and then inserts them into the circuit board. All right. So those are tantalum capacitors. All right, and again, those come in all kinds of different sizes and shapes, and sometimes they have writing on them, sometimes they don't. So let's take a look. Here are a couple others. All right, and there's another little tantalum capacitor, and this one I believe doesn't have anything on it. Nothing. No writing on that. So if you do not know what the value of this thing is, you are in trouble. So you're going to have to use a capacitance meter, or you're going to have to put it in a circuit, and you could maybe calculate what the capacitance is if you really wanted to. Here's another one, this little orange one. These are kind of cool. And so this one is 5 volt. There's the plus side, and the minus side must be the other one. And this is actually 1 microfarad. You can see that little one right there. And again, they give you, there's no love here when they put the values on these things. If you don't know what it is, sometimes you are in trouble. All right. So anyway, let's take a look. Let's grab our meter again. Let's grab our meter, and let's see if we can measure the value of this one. Okay. All right. So we're back over here. Okay, so we're back over here to the main area, main screen. So let's go grab a meter that can measure capacitance. All right, and let's see what we can come up with here. All right, so let's get this one. So this one has a capacitance checking function, or measurement function. All right, so let's turn this on, and if we look around here and we look around at this dial, right here is the capacitance measurement. And so all we need to do is put it on that right there. So turn it on. All right, so our meter is on, and see it's measuring now in nanofarads. And again, on meters, and we're going to go over this, we have a range button here. And if I press this range button, it's going to start changing. So we're kind of giving it an idea where we think this thing is. So microfarads, tens of microfarads, right? So I think this thing is probably a microfarad or so. So let's put it on that range right there. Okay. And then what we're going to do is we're going to, let's just back out a second so you can make sure you're seeing everything here. And then the leads are just in here. And we're just going to grab these leads. All right. And here are our leads. So we're going to come back here so you can see the screen a little bit better. And we're going to take our capacitor here. And now, when we're measuring this, we also kind of, if it's a polarized capacitor, we want to measure it in the correct way. So I can see that the lead on the right is the positive lead, so I'm going to bend those out. Now again, I have a lot of capacitance in my skin and so forth, so we want to try to kind of hold one of these on and then just kind of touch the other one. All right, so let's give that a try. So we're going to touch this on here. All right, and sure enough, it says 1.1 microfarad, and we believe that this is about 1 microfarad. So this is correct. Now, the one thing about these different capacitors and these different kinds of technologies, whether it's ceramic, electrolytic, whether it's tantalum, and there's all kinds, polystyrene, there's mylar, the list goes on and on. There are quite a few. You can Google it and look at it. They all have certain tolerances. Maybe the tolerance is 5%, maybe it's 10%, maybe it's 20%. So this one right here is probably 20%, 10%, and that's why we got that 1.1. So that's completely fine and tolerable, and we're happy with that. All right. So, okay, so that's the end of that one right there. So we're going to take our meter, turn it off. A lot of meters have auto off functionality, but it doesn't hurt to turn it off so that you kind of save those batteries. Okay, so, all right, let's continue on and look at some of the other components. All right, so what else do we have in our little list here? So we've got resistors, capacitors. Okay, so let's take a look at inductors. So what is an inductor? So an inductor is a device that is basically nothing more than a coil of wire. All right, so let's take a look at some of these. So let's come in here and let's zoom in. All right. I think we can get away with about that before this thing freaks out on us. Okay, so here, transistor got in there. All right, so these are all inductors. And where's our other inductors here? Here, we got this, and we got this. Oh, and just to show you how big, I just wanted to show you this. Back to our capacitors. Here's another capacitor. Look how big that is. So what is this? 25 volts and 4,700 microfarads. Look at that. That's cool. And then here's another one. So these are ripped out of power supplies. So I'll tell you one thing. Most electronics are kind of useless to rip apart devices and take them. But these big capacitors are useful if you need big capacitors because they're fairly expensive. I mean, it's made out of matter, right? So you got to pay for it. So these are big capacitors. So you can grab these out of an old power supply or something. If they're still good, definitely take them, desolder them, and keep them. And then, and then real quick, here is another. This is a AC capacitor. This is called an XY capacitor. And so this is used in AC circuits. So this can withstand AC, very high voltage, and it's usually very small capacitance. So this is like 0.47 microfarads and 250 volts. So that's an AC capacitor. All right. And then before we move on, this is a precision resistor. And actually, let me show it to you over here on the zoomed in. So this is a precision resistor. So this is only 0.01 ohms, right? Now, why on earth would you want a 0.01 ohm resistor, right? Well, that's usually to current sense. So in a circuit, there'll be a current flowing through some part of your circuit. And you put this teeny tiny resistor in here. It'll have no effect on the circuit, but it'll generate a small voltage, and then we can sense that voltage with an analog digital converter, and then we can compute how much current is flowing through the circuit. So we don't really know about voltage and current and all that, but that's kind of what these are for. So this is 0.01 ohm, and it's 1%. That's very, very accurate, and it can handle 3 watts. So this thing can dissipate a lot of power. All right, so that's that. Okay, so let's come back to our inductors here, since they have the floor. So all inductors are coils of wire. All right, so you take wire, you coil it up, and you've got an inductor. If you wrap it around something that has magnetic properties like iron or ferrite, then it'll have more inductance. Okay, so we've got 3 of them right here, and then let me show you. So here's kind of what's going on the inside right there. So there's other inductor, and this is inside of this is actually ferrite. It's actually iron. All right, and then I wanted to show you this because I just kind of want to show you how things come. So when you buy these parts, all right, so this is from DigiKey, and so it says choke, that just means inductor, 68 microhenries, 20%, and it's made out of ferrite. So you're going to have bag after bag, box after box, you're going to have countless little parts, all right? So it's important to, keep things organized, or you will go nuts, like actually crazy. Okay, so let's take this out. And let's go ahead and let's look at it. Let's look at these all zoomed in so you can kind of see what we have. All right. So this right here, so this is an inductor. So this is pretty cool. So now the first thing is the center of this is made out of iron or ferrite, okay, powdered iron. And it has certain magnetic properties that increase the flux linkage and make this a better inductor. And then you can see the wire comes in here, the lead, and then it's going to this wire here and it's wrapped around here so many times. So the inductance is proportional to how many wraps, how many turns. It has something to do with the material also, the ferrite, how many turns, and the diameter of the turns, and then the diameter, thickness of the wire, how much current can flow through it. So all these things have to do with how you compute the inductance. All right, but now this is kind of weird. So this wire is just touching each other, right? It looks like it's shorting. Actually, it's painted, or it has a kind of a tarnish on it. So there's a coating on here, and that protects the wire. So that, and the reason why we do that is we want to wrap these things as tight as possible, so there's no insulation other than a thin coating. And maybe that coating is, you know, a couple thousandths of an inch thick, all right, and or a thousandth or even less thick, and that protects it so there's no shorting. But you can get more coils in the same amount of space, because if you have insulation on the wire, then you're not going to be able to do that. All right. So again, this is this right here is an inductor, and we can see what's going on here. All right. So and this one's called, and this component we talked about radial. This one's axial, right? So it's axial because it goes on an axis. All right. So that's a pretty big inductor right there, right? Okay. Here's another inductor. And this is the exact same on the inside. So if I were to pull off, this is rubber sheathing on here. If I were to pull this off, you would see this thing is wrapped in here. All right, and there you can see we've got our two leads, and you can actually see the wires going from the leads, a little wire right there in that corner. All right, and then if you read this again, these things have all kinds of different encodings, and but this one is probably 2 something, right? And what this means in this case, it's 2 are the first two digits, and then this is 10 to the 1, or times 10. So this is 220 microhenries, I believe. Not 22 microhenries, I believe it's 220 microhenries. Again, if you forget how to read them or you haven't played with them in a while, you just get your meter out. That if you have an inductance meter, and then you just measure it, okay? But the values are on there some way, and sometimes there's no value on there, all right? Okay, so there's that. Now here's another one. This is another inductor, and this is called a ferrite bead. And you can see we just got ferrite, this material, and then we just got a few turns in here, and then this goes in a circuit. And these are typically to reduce noise, right? Because inductors have certain properties to signals, and they like blocking high frequencies. So this is good to block high frequency noise. So there's one right there, and then here's another one, even smaller. Right, and it just goes just so right here in this one little area. This is going to be more inductive because of this ferrite. All right, and there's going to be flux linkage, and so you're going to get a stronger inductor, even though it's just one wire. So every wire has inductance. So every time a current flows through a wire, magnetic field is generated. All right, and so but when you put this ferrite on it, it changes the properties of that. All right, so again, that's axial, and let's see. I think that's about it of those. So we've looked at a number of devices that were all through hole. So everything so far is kind of through hole. All right. Let's take a quick look here at something that is not through hole, something that is kind of surface mount. So again, when we look at, so let's take a look at, let me show you this little circuit here. So here's just a little power supply I did. And you can see we've got all these components and these little weird little rectangular solids. These are all surface mount devices. So, you know, here's a capacitor. These are resistors. Here's an integrated circuit. There's an inductor. That's actually an inductor. And there are also some through-hole parts. So what's through-hole? So this is through-hole, this little terminal block, this little switch, and see, and basically there's holes drilled through here, and they're soldered on the other sides. Okay, so this is what a surface mount inductor might look like, right? And here's what a surface mount resistor. So you see they're tiny, and they get very, very, very tiny. They get so tiny, in fact, it's very hard to work with them because you will lose them. All right, so for example, let's go back over to the big screen here. Let me show you this. Let me back out of this for a second just to show you. So all right, so when you start doing electronics, you're going to need to store them somehow. So this is just a little case. Let me back up a little bit more so you can see it maybe. All right, so this is just a little case that holds the components. All right, and so what is in here? Uh-oh, wow. So yeah, believe it or not, I sat and all these components, let me zoom in a little bit for you. All of these components I took from little holders, little packages, and then I took them out and then I put them inside of all these little boxes. So if I open up one of these little boxes, the little components will be inside of here. And I want to show you just how ridiculously small these things are, okay? Ridiculously small. So in surface mount technology, there's a number of different size delineations, and the numbers have to do with the dimensions in millimeters. Anyway, the sizes kind of you're going to see use most are 805 and 603. 805 and 603, then it goes down to 402, and then it goes down to 201. So 402 is at the point that most people can't with their eyes even work with them. So most people will work with 805 or 603. And again, we'll look at that more when we get to it. Once you get to 402, they're just too small. Then there's 201, which are ridiculously small, and then there's even 100 series that are even smaller than that. So let's grab, just to show you how nuts this is, and we'll use the tip of a pen to kind of give you some reference. So let's grab an 805. So if we look around here, let's see what we got here. So here is a, let's find something good that's 805. All right, so here's a 4.7K 805 resistor, all right? And you can only write down so much here. So there was probably a tolerance in the type of material it was made out of and all that. But anyway, I'm going to open this up, okay? And I'm going to grab one of these out. And this is just ridiculous how small these are. All right, I'm going to put it on the tip of my finger, all right, which you cannot see very good. Now I'm going to move over to the zoomed in camera. Okay, and there it is. Okay, so that is the teeny tiny little part. And let me grab it again with the tweezers. All right, this is not easy to do with this camera. All right, so there it is with the tweezers. Let me back it out. Okay, so look at that, and there's that giant tip of a pen. So this is, you can see the number on there, 472, and let me get it back and zoom. So it's 4.7 times 100, so that's 4,700, right? And that's the 2 is again the multiplier. So the smaller they get, they have no writing, and so if you lose it, you have no idea what the value is anymore. Okay, so if you lose the packaging or you forget what the value is, you have to measure it. All right, and again, how do you measure something like this? Well, just like we did the other thing, you just and here's another thing. When you're dealing with things this small, stiction and different physics properties wonderfully come into play, and so you're like working on something and then you're like, where's the surface mount component? Well, it probably stuck to you and now it's on the floor, on the carpet, and you will never find it. So if I want to measure what that value is, right? So, oops, if I want to measure what that value is, let me zoom in a little bit. Let's see if I can get it to cooperate a little bit. Oh, that's not bad. And I'm going to turn it around. Okay. Turn it around. Okay, crazy, crazy. Okay, so now let's get one of our meters. And I'm going to get a meter that has sharp probes. All right, and let me see. I think this one's sort of got sharp probes. Okay. All right, so now what I'm going to do is I'm going to close up the surface mount components, and we'll put our meter over here, and we're going to kind of go back and forth. So we're going to set our meter, so it's 4.7K is the value, so we'll put it on 20 kilo ohms range. And again, we really don't know what an ohm is and all that, but just bear with me. All right, so we've got that, so we got our meter, and now we're going to come over here. And so I have 20/20 vision still, and this stuff is impossible to see. So right now, when I work with surface mount electronics, I wear magnifying lens glasses, and so that these will really help you. So this kind of stuff you can wear, and you can just get these at a store. Or if you want to get crazy and steampunk, I wear these kind of things, and they have lights on them and stuff. So those are really cool. And these are super magnifying glasses, so those are really cool. All right. Okay, so let's try and put these probes up here, and let's see if we get 4.7K. All right, so it says 4.7K. It looks like 4.7K, so let's see what we got. So we put it up there, and ever so gently, and then watch the meter, and 4.68, yep. And this is probably a 5% resistor, so it's within tolerance. And again, there you go. Very nice. And that's how you do it. So if the number's on there, great. Okay, so you can read that. Now, let's assume that we want to go smaller. Okay, we want to go smaller than that. So we're going to put this back. So we're going to go back to our surface mount case here. We're going to open this back up. We're going to find the 4.7. There it is right there. We're going to put that back in there, make sure it's off our finger. Okay. And now let's see if we can find something else. Let's punish ourselves even more here. So let's find something even smaller. So let's find a 603 size, even smaller, and something. Let's look at a capacitor. So we'll find a 603 capacitor. So a really common capacitor is, let me see if I got it on screen here. Yeah. So see this 0.01 microfarad? Let me see, do I have any in there? Yeah. So 0.01 microfarad is a really common capacitor used in circuits that we use a lot. So let's grab one of these. So we're going to open this up, all right, and I'm going to go in here and grab one of these. And this is even ridiculously more small, okay? So there it is there, and you cannot even remotely see that. So now let's put it under here, all right? And there it is, and I'm gonna zoom out a little bit here. Okay, so there it is. So now again, let me show you the tip of the pen to give you some scale. So, you know, and so this is just horrible. And then when you're building something, let me get you another little circuit board here. Okay, so here's another little circuit board, and this is all surface mount. So this is a little charger that I designed, a little USB lithium-ion battery charger. So now, you know, looking at this, here's the capacitor C2, and this probably takes a 603 size footprint. So you can see we just put it right on there, and so you would place it right on there, all right? And one way or another, you need to solder that on there. Okay, that's why when we're doing electronics, a lot of times we'll start off and do through holes design only, so that we don't have this problem, because this is really hard to do. All right, and but there are different ways to do this. All right, so let's take that, and usually you just kind of, it'll stick to your finger because of moisture. So we'll take that, and we're going to put that back. All right, so let's go back over here, and hopefully we can find it. Here it is here. Put that in there. Now, have I ever dropped this? Yes, but these things all close pretty good, and I keep this thing closed. But I can't. If you lost all these and they got on the ground, you would never get them back together. Okay. Now, let's go back and we got a couple more things, but I want to show you something else. So here is this board is completely through hole, completely through hole. All right. So you can see that, and let me zoom just a little bit here. And let me turn that around. So this is a through hole so that you know, people can build this, and so you put all these parts in here and you solder them. So, but typically most people, well, I don't think anyone's made a professional product in decades that is not completely surface mount. Everything is surface mount now. Everything is surface mount. They'll have some mechanical components that'll be through hole, but you have to do it. Look at these chips, right? Look how fine those are. Let's go to the small. Yeah. So you can see that's no fun there. All right. So that's a processor, another processor. You can see how small everything is, right? So robots build this stuff, but you can build it too. You know, I build stuff this size all the time, not a problem. Here's another board. Again, this is all surface mount except for the through-hole components, because they need to be mechanical to plug into something. Okay. Okay. So what else we got? Diodes and transistors. Okay. Last two things. Last two things. Okay. So let's take a look. So here is a transistor. All right, let me zoom in a little bit on this one. Let's see if we can get in here a little bit. Okay, so there's a transistor, and we'll go real close to that in a second. All right, and a transistor is an amplifier. And again, you know, how do they come? So these are through hole, so they're going to come in this kind of tape, and they'll be removed from the tape by a machine and then inserted into the circuit board. All right, so if we go look closely at this, let's go over to the other screen here. We can look at this, and if I get the light just right, you can see, so it says PN222A. All right, so this is actually a NPN transistor, and we'll learn what the N's and the P's mean later. And a transistor has three leads, a collector, a base, and an emitter, or emitter, base, and a collector, depending which way it goes. And again, which way does it go? You have to look up the specific manufacturer. It may go one way, it may go the other. All right. So that's that. And again, you have some idea of scale. All right. So that's a transistor. Now let's move over and let's look at a diode. So let's look at a diode now. So there's a diode on the big one. So there's a diode there. Here's another diode here. And then diodes can get very big. So diodes are semiconductor devices, and they allow current to flow in one direction. All right. So let's take a look at what these things look like up close. So come up here, and again, let's see if we can get the right kind of lighting here. It's always a little bit hard. All right. So it's very specular, but if you look at this, it says 1N4001. This is a very common, famous diode, the 1N4001. All right, and this is a silicon diode and allows current to flow in one direction. Conventional current, which we're going to learn about, will flow from this side. This is the anode, and this is the cathode. And the cathode always has this stripe on it, this white stripe usually. Conventional current will flow from left to right here. All right, electron current flows from right to left, but we're not going to talk about electron current when we actually do things. But we'll figure what that means in a while. And here's another diode. So this one is called a glass passivated diode. Let me bend those up a little bit, clean those up. All right, and again, you can look on it, and you can see the number on it, which even under this magnification is difficult to see. But anyway, the cathode is to the right. You can see the black bar. So again, current is going to flow that way. All right, and these have slightly different properties, and the value has to do, the part number has to do with how much current can flow depending on the manufacturer and voltage, things like this. So these, and sometimes the part numbers are just completely random. All right, so anyway, those are a couple diodes, and that's what diodes look like. Again, these are axial diodes, and you can bend these leads. You got to be very careful. A lot of these are made out of an aluminum alloy, and you bend them a few times, they're done. They're not meant to be bent. They're meant to be bent one time and then inserted into a circuit board. So if you're going to use these and you're going to put them into your solderless circuit board and work with them and all that, you have to be careful, right? So again, we can zoom out here, zoom out a little bit, and we'll bring our solderless circuit board, which we're going to learn about this shortly. But again, we're just going to kind of jump into it. And so what I'm going to do here is I'm going to take this and I'm going to bend it right at that joint. Do it like I mean it. Don't, just kind of do it a little bit. Just do it, get it done with. Now, another thing you're going to notice, the ends are blunt, and they're going to make mechanical contact. There's little clips inside of here. So these wires are common like this. These clips allow current to flow in these columns. So if you put it here, this is all connected, right? If you look at these closely, they're little clips, and when you push something in there blunt, it's going to catch it, all right? So what you typically do is you might even take some sandpaper or a file and file these down a little bit and kind of make them, kind of chamfer them, and they'll go in a little bit better. So I'm going to put this one, I'm just going to put it right in here. And again, do it like you mean it. So I'm pushing it not too hard, kind of wiggle it, kind of, roll it around, got to, kind of work it in, and it's not very easy. So like right there, it's really binding, right? So not making me happy, and I'm probably messing the board up a little bit. And again, I'll do it here, trying to get the camera angle so you can see it. And oh, see, it bent. So right now, this is telling me, hey, you need to really chamfer these a little bit and clean these ends up so you can kind of push them in here, not damage this board. Because what you're going to do is, when we're building things, we're going to take wires, all right, and let's find a little wire here to kind of show you. We're going to take wires, and we're going to plug these wires in to this board, and we're going to connect things, right? So like say we wanted to connect those 2 points. That went in really easily, right? So, but if I open these things up by putting parts that don't fit, right, then I'm going to damage this board over time. So that's why if you want to put these in here, you're going to have to chamfer these and get a little file. A little nail file works really good, that kind of thing, or a little bit of sandpaper, and just take the sandpaper and put it down and just go like that, go like that, all right? Real world stuff, all right? But we're going to get to that when we get to that more. Okay, so what else do we have? What else do we have here? So we did transistors, we got batteries and wires. We already know what those things are, so don't need to worry about that. All right, so I think we've done about enough. And in the next lecture, we're going to do digital electronics, and we're going to talk about some other things so that we have vocabulary to talk about electronics. And we're going to start, getting a little bit into more of the theory now that we've kind of had kind of a hands-on section here, and we kind of see things and see what things look like. All right, so I'll see you in the next lecture, and that's it. Bye. And discuss a little bit more about digital electronics. And again, we're going to repeat these things over and over as we go through the lectures and talk a little bit here and a little bit there, so you can kind of get a good feel for what's going on. So we're not just going to do this once and then forget it. We're going to keep doing it and try and make connections to other ideas and concepts. All right, so primarily in this lecture, we're going to talk about digital electronics a little bit. We're going to do some hands-on stuff, take a look at things. We're going to talk about the units of measure and that you deal with electronics and electrical engineering. We're going to talk about some atomic theory, and don't worry about it, but we need to talk about it just so that we can kind of have, again, a language and a vocabulary to understand what current, what voltage, what power, what all these terms actually mean. And I just want you to know them, someplace, somehow, a little bit, in the back of your head. You don't have to master these things, but it's really going to help so that, again, you're just not blindly connecting things together and not really understanding what's going on or even knowing where to start if you wanted to figure something out. All right, so anyway, so let's get started. And so take a look here on the screen and let's see what's going on here. So the first thing, let's get a little cursor thing going here so we can see what we're pointing at here. All right. So digital electronics, let's talk about this. All right, so digital electronics is based on analog electronics. So everything is analog ultimately, except with digital electronics, instead of worrying about continuous signals and signals that vary over a continuous range, we're only worried about kind of two states. All right, so digital logic is a two-state system. So things are either on or they're off. All right, now there's lots of different kind of two-state systems in digital electronics that are based on voltages, and the most popular that you'll kind of bump into when you first learn about electronics is a 5-volt system. So a digital 0 is 0 volts, and a digital 1 is 5 volts. All right, but there are other systems, all right, and other voltage levels, all right. So these are just values and amplitudes. All right, so taking a look here at this kind of figure that we have on the screen. So again, we see our square wave here, and we have one signal up top, and these signals are both digital, and one signal up top is kind of going 1 0 1 0 1 0 1 0, and it's happening at some frequency, and it looks like it's periodic and repeating. And it's going from 0 volts to 5 volts, which we've mapped 0 volt and 5 volt to 0 and 1. And again, we're not quite sure what voltage is. We're going to learn it specifically. And then down here, we've got the same thing going, where it's going 1, 0, and then 1 for a long time, 0, and then 1, and then 0. So these are digital signals. Now, of course, all signals are analog signals. So this is an analog signal. That's a square wave, and another kind of a square wave that's non-periodic. But we're going to say that these things are digital signals, and we're analyzing digital systems. Okay, so how we build a digital system is we use analog blocks, switches, amplifiers, and so forth, so that we can create a model that allows us to process information as ones and zeros. And these ones and zeros are represented by voltages, 0 volts and 5 volts, or 0 and 3.3 volts, or 0 and 1.8 volts, and there's many other voltages. All right, but primarily 0 and 5 volts and 0 and 3.3 volts are the kind of two most popular systems you'll see. All right, so and everything these days is more or less digital. All right, computers, calculators, LCD watches, video games, all that stuff. Now, even radios now are digital. Software-defined radio, everything has been kind of converted into the digital domain. So what happens is the real world is analog. The real world is continuous, it's messy, and it's all over the place. So how we've converted everything digitally is at some point we have to acquire this analog information, this varying continuous information, and bring it into the computer or something to process it. So we can use an analog digital converter, and that's something we'll learn about, and it converts that analog signal into a digital signal, and then we can process it as a digital signal, as numbers, as numbers. And now, of course, when this happens, you've digitized something, you've sampled it, and now there are errors that are going to be incurred. So here's the interesting thing. Digital systems are never 100% accurate, right? Because they're always an approximation of something that's kind of occurring in the analog domain. But depending on how much accuracy you need, you can tolerate the amount of error, right? So for example, say if you're going to make something that's going to record voice and playback voice, right? Say an MP3 player. So first we have to have a representation of the sound, right? So we might have a digital representation of the sound, and then we have to play this sound back. So three different things are going to cause an error here. So first we have to sample the sound. That's going to cause errors as we take the analog signal and convert it to a digital signal. Then we're going to store this, maybe compressing it. Now we've incurred even more errors. And now we're going to play this thing back. And again, during the playback system is going to take this digital information and convert it to analog, because that's how we process information, So all these different things are incurring errors, but the digital processing is at such a resolution and speed that these errors don't make a difference to us, or we can't hear them, or we can't perceive them, or we can't even measure them for that particular problem. All right, so keep that in mind. So everything's analog, and we can convert these pieces of data and information into digital approximations and then process them much, much easier. That doesn't mean that analog computers don't exist. The first computers were analog, and analog computing still exists in some ways, but typically everything is now digital. Even things that you would think would be analog are digital. Now, some things aren't digital, like a power supply, for example. That's just an analog device, but it'll have digital components in it, maybe for control or something, which is interesting. All right. Okay, so let's keep going here. All right, so now, again, we're going to have to start talking about voltage, current, and all kinds of different electronic parameters. And to do that, we have to have a vocabulary, and we all have to be on the same page here. And one of the most important things is units of measure. All right, so this is going to be a little, high school refresher, college refresher, if you don't remember. But so the couple systems here. So the system that we use, and the majority of the world uses, is called the International System of Units, or the SI system. All right. This system, some of the units are shown in this table here, right? And then, of course, there's also the English system, which is kind of all over the place. But we're going to use the SI system, or International System of Units. So in that system, time is measured in seconds, length in meters, right? Not yards, not feet, not inches, meters. Mass is in kilograms, force is in newtons, charge is in coulombs, all right? And so now, these things most people have a feel for: time, length, right? Mass. Mass is the amount of matter, and don't confuse that with weight, right? Weight is a force, so be careful. So mass is matter. In the English system, a lot of people don't know the unit of mass. It's actually called a slug, all right? Anyway, but mass is, if we go over here, kilogram, and then force, newtons, right? So these aren't pounds, these are newtons, and this is 1 kilogram times meter per second squared, all right? Charge is coulombs. Okay, so charge, this one is sort of, understandable. This is a number of electrons, so it's 6.24 roughly times 10 to the 18th electrons, okay? So that's a coulomb of charge, all right? Energy is a joule. Now, once we start getting into energy, energy is fairly abstract. Energy is the ability, something to do work. So this is 1 Newton meter. So this means 1 joule is 1 Newton of force applied for 1 meter. All right, so again, that's very abstract, doesn't mean a whole lot. It's hard to wrap your brain around. Okay, current is measured in amperes. A is the symbol, and this is 1 coulomb per second. And again, we're going to go over these things a bunch of times. I'm just kind of, running down here. And so that means 6.24 times 10 to the 18th electrons are going to pass a point in 1 second. That's 1 ampere, all right? So that's a lot of electrons. All right, next thing is, now this is where things get really funky. So a volt is 1 joule per coulomb. So this doesn't have a whole lot of meaning right now. So voltage, you can think of it like a pressure, but its actual units are joules per coulomb. All right, which is kind of strange, but we're going to, in a little while, kind of see the derivation of that, and so that'll give you kind of a basis of what's going on. And then power is measured in watts. So like your light bulb is 10 watts or 20 watts or 100 watts, or your computer uses 500 watts or 1,000 watts or 1,200 watts. And that's a joule per second. So this is energy expended per second. So you can see that voltage and power and amperes, a lot of these things are very related right here, right? Coulombs, seconds, joules, right? So they can be converted from one to another fairly easily. Okay, all right. And then, you can read through all this stuff, these notes, but, I like to give just, one time, just say it. So force is measured in newtons, and that's after Sir Isaac Newton, of course. All right, and then 1 Newton is equal to the amount of force needed to accelerate a mass of 1 kilogram to 1 meter per second. All right. A Coulomb, standard measure of charge, is Charles Augustin de Coulomb, and 1 Coulomb, of course, is 6.24 times 10 to the 18th electrons. All right. Or here's another interesting way to think of this: 1 electron, right, would be the inverse of that. So 1 over 6.24 times 10 to the 18th. Would be the charge of 1 electron. So it's 1.6021 times 10 to the minus 19th coulombs. So in other words, 1 electron has a teeny tiny little charge, very little charge, all right, to the minus 19th. Okay, joule, again, this is a James P. Joule, and joule is the amount of energy of work, a 1 Newton force applied for 1 meter of distance. And that's it. And again, a lot of these definitions seem very circular, but that's just the way it is. All right. And then ampere, we talked about this. Current is measured in amperes. So current is the actual matter flow. It's the actual motion of electrons, right? And that's after André-Marie Ampère. And 1 ampere is equal to 1 coulomb a second. And we know a coulomb is 6.24 times 10 to the 18th electrons. So that many electrons pass a point, and that's a coulomb. And then now here the volt, and this is voltage is kind of hard for people to understand because the fundamental units don't make a lot of sense. You got to look at the kind of field theory to kind of really get a good grasp on it. But it's like pressure. It's what pushes the electrons. All right, so this is called the electromotive force. All right, and volt is named after Alessandro Volta. All right, and there's a couple ways to kind of measure this, and we can look at it in different ways. But one way is, and it says it right here in the text, if you were to move 1 coulomb of charge while expending 1 joule of energy between any 2 points, then that potential difference is 1 volt. So that's kind of interesting, right? So 1 coulomb of charge, and you only get to expend 1 joule of energy moving it. That would be a 1 volt potential difference between those 2 points. All right, so you can kind of put things on different sides of the equation there. All right, let's keep moving. And then finally, the watt is named after James Watt, and watt is the measure of energy expended per second. All right, and it's just joules per second, and one watt equals 1 joule per second. So that's fairly easy. So once you get a grasp on a couple of these fundamental units, these other units are just products or quotients of them, and mixtures of them, and you can kind of break it down and kind of get a little bit of a feel, but it's not easy. I mean, if you ask a physicist what's energy, what's time, what a lot of these things are, ultimately these things don't make a whole lot of sense. What's inertia? What's mass? What's energy? So anyway, all right. Now let's talk about the SI system of prefixes here. All right, so the first thing is when we're dealing with electronics and electrical engineering, embedded engineering, the number is going to get really big and really small really, really fast. All right, so if you're not familiar with scientific notation or you don't remember it, it's just a way of normalizing the numbers so that there's kind of a base and a multiplier so you can kind of deal with them. All right, so this kind of explains kind of what's going on here, but the bottom line is you have kind of what's called a mantissa times 10 to an exponent, all right? And then you can represent numbers in kind of a normalized fashion, all right? So so as a matter of fact, we'll get into that in 1 second, do some examples. But before we do that, let's look at some of these prefixes. Now, some of these you'll be familiar with. So if something is just, unit, right? So that would be 10 to the 0. 10 to the 0 would be 1. All right, so if something's a thousandth, that's a milli, right? A millionth, right? 10 to the minus 6, there's micro. 10 to the minus 9, or a billionth is nano, and then a trillionth is pico, all right, and then a thousandth trillionth is femto, and then up here, 10 to the minus 18th is a very small number, is atto, and then here are the symbols for them. And then again, these will be kind of familiar. So if you have 1,000 of something, that's kilo, and then a million is mega, 10 to the 6th, and giga, 10 to the 9th, tera, 10 to the 12th, 1,000 tera is a peta, right? So now we're dealing with computers that are petabytes, and storage that's petabytes. And then we have exabytes, or excuse me, exa here, 10 to the 18th, which is E. All right. So, all right. So these are kind of the common prefixes that you can use, so you can simplify things, and I have to put this this value. All right. So let's do a couple examples. So in this example right here, we've got 3.0 times 10 to the 4th watts. All right. So so 10 to the 4th, that would be 10,000. All right, so let's actually come over here and let's take a look at this. So 3.0 times 10 to the 4th, let's kind of make sure that we get what's going on here. All right, so we've got 3.0 times 10 to the 4th watts. All right, and so this is already in scientific notation here. But this 10 to the 4, this isn't this isn't one of the common prefixes, right? So 10 to the 3rd, that is kilo, right? So we could use that. And then mega would be 10 to the 6. So what we want to do is we want to kind of get this into a form that would allow us to use one of the prefixes here. Okay, so this is 3.0 times 10 to the 4th. So a number of different ways to do this. So one way to do this would be if we take the decimal point and move it 1 to the right there. Now we've multiplied this side times 10. Okay, so now we need to divide the right side by 10 so that the number stays the same. So now instead of 10 to the 4th, it's now going to be 10 to the 3rd. All right, and what we did was if you look at this, we said let's multiply this times 10, but if you do that, then we need to divide this side by 10, because times 10 divided by 10 is times 1, so the number stays the same. All right, so we multiply this side times 10, and then we divide this side by 10. All right, and then when we do that, we end up with a 30, and then we do that, we end up with the 10 to the 3rd. All right, so now what do we have here? So now we have 30.0 times 10 to the 3rd, but 10 to the 3rd, kind of come back here, and we know that 10 to the 3rd is kilo, right? So that must be kilowatts. So now we can simplify this. I'm going to say 30.0 kilowatts. Okay, all right. So more specifically, and then if you want to kind of mess around with the exponents here, so remember a couple things, right? If you have numbers of the same base, all right, so you have the same base, say 10 to the x, and you have 10 to the y, this and this is, these are called the base, right? And these are the exponents, right? So 10 to the x times 10 to the y equals 10 to the x plus y. So you can just add them. And if one of these had a negative sign, then you would just add the negative sign. All right. So when you do these conversions, you can kind of keep this in mind. You kind of keep this this thing delineated. So you've kind of got the whole part here, and then you've got kind of this exponent part here. This is mantissa. This is called the exponent. And then you kind of convert these to make them into more reasonable values. Now, so let's look at, go back here, and you can see, so in this example, we wanted to use the kilo prefix, so that's 30 kilowatts or 30 kW. Now, if we wanted to use the mega, right, so it's 0.03 megawatts. So kind of, how do we get to that? So let's take a look there. All right, so once again, let's start off, and we're starting off with this 3.0 here. All right, so we've got 3.0 times 10 to the 4th watts. All right, I'm just going to say W for watt. All right, 3.0 times 10 to the 4th. What we really want is 10 to the 6th here. Okay, so I want 10 to the 6th. So I need to multiply this times 10 squared. That would give me 10 to the 6th. All right, so why is that? So if I have 10 squared here, and I multiply times 10 squared, we're going to add these exponents. So now we're going to end up with times 10 to the 4 plus 2, all right, which is equivalent to times 10 to the 6th. Okay, so that kind of handles this side. Now on this side, we multiplied times x squared. So that's basically times 100. 10 times 10 is 100, right? So over here we have to divide by 100. So we got to divide this by 100, all right, which is equivalent to moving the decimal place to the left, right? So we're going to move the decimal place 1, that would be divided by 10, and move it again, all right? So when we're done here, what we're going to end up with is 0.03 times 10 to the 6. So let's write this all down cleanly. Okay. Okay, so now we have this value here, and so now we can turn this into, this is one of our prefixes, this is mega, so now we can say 0.03 megawatts, all right? Now, typically you won't see that unless someone said, I want you to write everything in megawatts and you want to work in megawatts. That would be your base kind of prefix or scaling factor. But typically what people will do with scientific notation is kind of do normalized scientific notation. All right, so in normalized scientific notation, what we're looking for here, let me erase some of this, is we're looking for numbers between like 1 and 10. All right, so whenever we have a number, so say we could have something that was 153.1259 times 10 to the 4th. All right, and that's a perfectly valid scientific notation number. But what if I wanted to say I want all numbers between 1 and 10? So I want to move this decimal 2 times to the left. So what I want is everything that looks like this. I just want this number right here to be no larger than 10. So 1.531259 times 10 to the, so now what did I do? I divided this by 10, 100. I moved it 2 times to the left. All right, so that's a smaller number, so I'm going to have to move this 2 times to the right, or multiply by 100. So now it's going to be 10 to the 6th. So now 153.1259 times 10 to the 4th is equivalent to 1.531259 times 10 to the 6th, or 1.531259 mega. All right, so that's normalized, and a lot of times it just helps because then the numbers kind of have one digit over here, and then they have a bunch of decimal places. All right, okay, so that's one example. And then another example here, we're just talking about amps, and so this is now using kind of a counter example where you have something small. So we have 5.0 times 10 to the minus 3 amps. So minus 3 we know is milli, right? So the milli prefix, so that's instead we can say it's 5.0 M amps or milliamps, all right? And then if we wanted to scale it to microamps, because maybe what we're doing is in microamps and we want to do everything in the same scale, micro. So if we have 5 milliamps, we must have 5,000 microamps, all right? And that's where we get this. So 10 to the minus 6, if we want that to be our prefix, we can't just arbitrarily change the base, so we have to change the number. So 5 milliamps is the equivalent to 5,000, because we multiply by 1,000 microamps, okay? Okay, all right, so that's our bases, some scientific notation, a little bit of discussion about digital electronics. And then before we go, next time we're going to come back and we're going to start on this whole thing here, atomic theory, electrons and holes. That'll be fun. But before we go, let's take a look at just some digital components again. And everything's going to be about repetition. We're going to see things multiple times, and then that way we can kind of get a feel for it. All right. So let's go take a look at some digital parts and kind of see what they look like. Right. What some chips look like. Okay. So let's take a look here. And everything in digital electronics are usually integrated circuits, right? Small integrated circuits, and they have certain kinds of packages. So let's zoom in here a little bit and take a look at what we got here. All right, and so this is one way that we kind of protect and hold little integrated circuits. All right, so let's take a look here. And all these little ICs here are integrated circuits, and we can just grab something here and see what it is, something interesting here. And okay, so for example, So this one right here, now, so the first question is, why is it on this foam? So this is anti-static foam, and this anti-static foam actually conducts electricity very lightly, all right, and actually has resistance. So if there's charge, right, on the component or on your hands, a current will actually flow inside of this and it will dissipate. Okay, and that's what you want. So this gets rid of a charge because it's conductive. So this is slightly conductive. And in a minute, I'll actually show you its resistance. All right, but here's an IC, and so you can see that this is got these kind of pins on it. All right, and each one of these pins has a certain pitch, a distance between them. All right, and then there's so many pins. This particular one should have 14 pins. And if we count on here, we'll see 1, 2, 3, 4, 5, 6, 7, and on the other side there's 7, so that would be 14 pins. So this is a 14-pin DIP package, dual inline package, right? And this is what digital chips and ICs come in, one of the packages. Now there are many packages and surface mount packages and all that. All right, so and then this particular chip, let's take it on the other screen here and get a real close look. So, all right, so take a look at that. So it says 74HCU04. So what this is a inverter package, and this is a CMOS inverter package. So inside of here, there are 6 digital inverters, all right? And every 2 pins is an inverter, inverter, inverter. Then there's a power pin, and power pins are typically at the bottom left of these kind of chips. And this is what you would call a CMOS or TTL chip. CMOS, complementary metal oxide semiconductor, or TTL, transistor logic, which we'll talk about later. But anyway, they all kind of have the same footprint, and the pitch is the same for these large dual inline packages. And these are easy to work with, and this is kind of what everything was made of in the 70s and 80s, right? And on the package, the bottom left pin is typically ground, and the top right is typically power, or what's called V sub CC. Now that's not a total rule, but most of the time. And then you see this little marking here, this little indentation. This marks the top of the chip, and then that's how you kind of find the pin number 1. So if you orient this up, this little groove, this little notch, this will be pin 1, and then the pins are labeled, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so they're counterclockwise. So they're always counterclockwise. All right, so that's just, one chip. All right. And let's go back here and see if we've got anything else interesting here on here. Let's see, another inverter. And again, you just kind of put them on here, and there's lots of different ways to store these. All right. And okay, so here's something interesting. So these little guys, all right, so we take a look at this one. So this is a much smaller package. So this is a PDIP 8 package, all right? And then what's on this, amazingly, is a microcontroller. So let's kind of come over here and zoom in. So this is a PIC microcontroller. This is a 12LF1840 microcontroller. This is a very powerful microchip PIC microcontroller. It has a lot of cool features. It's got an internal clock and all kinds of peripherals. And so there's a whole computer in this little chip, which is amazing, right? And the signals, each one of these pins, there's ground and power, there's programming pins, and there's all these peripherals. And what happens is these peripherals are multiplexed on these pins. So you can say, hey, I want these 2 pins to be input-output pins, and I want these 2 pins to be maybe a I2C or a SPI. And that's those are 2 kind of communication protocols that are used with processors and microcontrollers. But again, this is a digital chip, right? And it's an entire computer on a chip. Now, so again, you're going to have lots of these things, and you have to store them. So, for example, here is, you can see another way, all right? And now, like I said, everything done today is more or less surface mount, but when you want to prototype, it's kind of nice to do things with these through-hole parts, because then you can work with them on your solderless breadboards. So if we kind of go through here, and I think I have this upside down. Yep. All right, we go through here and we can kind of look around and see things, what the different chips are on here. And there was a time I had everything memorized, 74. So like this chip over here, This is a AND gate, so this is a 74 LSO8 AND gate. So this is a quad AND gate. Come over there so you can kind of see it. So this is ALS. This is Advanced Low Power Schottky. And these technologies, this TTL technology, you still use it today, but now we've got low power TTL and low power CMOS. But these are, you're going to still use these to prototype and learn electronics with, and they're very robust, and they're you know, they can tolerate over voltage and things like that. All right, so again, you know, we see the notch up there. This is, again, this is a 14 pinner, and so there's pin 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's ground, and there's power up there. All right, and then now the important part is these things will plug in to these solderless breadboards, which makes them very easy to prototype with. So say we want to do something, we wanted to kind of put our AND gate down and our inverter gate, we would just put it down, and then it presses right in there and just pop it down, all right, carefully, and now it's in there. And then I'll take it out, and let me show this to you up close. You can kind of see. So this is our solderless breadboard here, and let me get it to kind of focus a little bit better. So you can see I'm just going to put this in, and now I'm not going to put it on this side because that would, these are all connected. Every column is connected. So we're going to put it like this, all right, and then we're going to press it in gently, all right, and now it's in there. And now we would hook something up to pin 1, pin 2, pin 3, and just wire things around. We'd hook, this is the ground pin, so these are all connected. So we take a wire here, and then maybe we put ground along here, and we're going to learn to do this. That would maybe be ground, and then the top pin here is power, V sub CC. So all these are connected. So we take this, and maybe we'd put power up here on the blue rail up here, or on the red rail, whichever. All right. Usually the red is for positive, and the blue is negative, but doesn't mean that. You can do whatever you want, just as long as you're consistent. Anyway, and then we would put power up here, we put power down there, and a couple other things, and now that chip is ready to go. It actually will work, all right? If you were to put 5 volts to this thing, it would actually work, and then you could make a little circuit out of it, all right? So that's kind of that thing. And then some of these larger chips, so this is kind of interesting here. So you see this particular chip right here, if I can look at this one and see the number on it. So I believe this is, yeah, this is an EEPROM. I don't know the size of this EEPROM. But so this is an old style electrically erasable programmable read-only memory, EEPROM. All right, and you can see there's a window here, all right? And so let's take a closer look at this. All right. So we come in here, and let's get the camera to get some good lighting here so you can kind of see. There we go. And okay, so that's nice. And if we turn it around, all right, so you see it says M27C2001. If you go Google that, you'll be able to tell exactly what this is. But what I'm more interested in is this little window here. So I'm going to zoom into this for you, and check this out. This is going to be cool. So this is the actual silicon. You're seeing the actual silicon inside there. And this is an EEPROM, so there's a bunch of memory cells. And how this thing works is you program this with a certain algorithm, and then the only way to erase it is with ultraviolet light. And to do that, you have to expose this to ultraviolet light, and then the high energy photons hit each one of the memory cells, and they cause the charge to deplete and erasing the memory. So when you don't want that to happen, you have to cover this. So you cover this with some tape or something that UV light cannot get through. All right, and so you won't see these anymore, especially a chip this big. But again, this is a kind of, you know, the basis of things, so you can kind of understand what's going on. And then again, you can look here at the comparison in size. Let's zoom back out. The comparison in size. So you could prototype something with this on solderless breadboard. You just have to be careful, and you'd put it in, right? And you got, now with big chips like this, you got to make sure everything's in. Then you kind of rock it in, very gentle, and then very gentle, put it in here and get it to bite. And then when you go up on the side, you can see that didn't bite down, right? It didn't get in there. Now, again, see, I'm prying it out with my fingers. That's not a good idea. So what we're going to do is use a tool. Let's find something here. There's lots of ways to do this. So let's get a good tool here. All right. So here's kind of a little flathead screwdriver. And then so what we're going to do is we're just going to put it under here while holding the chip, and we just kind of gently pop it up. and then rock it. All right, and so now it's out of the socket. So again, I would look here and, oh, you see that? See how those are kind of trapezoidal? They're coming down at angles. So what I might do, and this is a brand new chip, I've never used this, I'm going to bend it here on the table a little bit, bend it, and kind of square those up a little bit. And now I might be able to get this in better. Okay, so let's try and put it down here. All right, and again, we would try and get it into 2 rows. There's a row and there's a row. It's not going to leave a whole lot of room for prototyping. All right, let's see. And of course, we're doing this live, so this is not cooperating with me. There we go. All right, there. Good. Okay. And there. And you don't want to bend those pins, of course. And that's why you got to be really, really careful with what you're doing. So that's in there really good. And now the only problem is that if we want to connect a circuit and do something, every one of these pins is only got 2 leads here, and this side's got 3 because this the solderless breadboard is only this wide. And there's wider ones that you can get if you're going to deal with large chips. And then again, the footprints of these things are kind of normalized. All right, so the width from here to here is kind of the same. This is one standard width, and then this is another standard width. All right, and so if you were to get a pair of calipers, all right, so if we were to get these guys, all right, let's turn this on, all right, let's put this into inch mode, and we'll tighten this up and we'll zero it out, okay, and then if we were to measure and kind of see where we're at here, so if we go there and we kind of measure from here to here, see that 0.3? This is actually a 0.3, so the pitch from side to side is 0.3 in reality, so it's a little bit smaller because I'm grabbing it at a little bit higher point, but it's 0.3, all right, and so that's that. And then if you come on this one, the bigger guy, see that 0.57, all right, so again, these will have different pitches in both directions, and that's how you can kind of tell the size of them. All right, so there's just some, digital ICs, just kind of give you an idea of what they look like and kind of how we store them. And then, as I said, you're going to have everything these days is going to be surface mount. All right, and then let me show you that real quick. Same thing, digital, some surface mount parts. And let's see if we have a good one, a good example of something with a bunch of surface mount parts on it. Yeah, let me show you something that's kind of ridiculously small. So take a look here, and let me zoom in on this a little bit. All right, let me get that to stop shaking. All right, so these are all surface mount parts, and so some of these there's some LEDs. Here's these are transistors, but again, each one of these parts has to be soldered onto these boards. All right, and so that makes that a problem. All right, and then to show you the level of integration, so let's find something really small here. So let's take a look at this. So you see this right here. So this IC is so small, and this IC right here, I believe, is a sound IC, and you can't see anything on there. It's just got a couple little numbers. This is a sound IC, and this is called a ball grid array, BGA. It's very hard to mount. It's microscopic practically. This is, I believe, 2 by 2 millimeter. And then so you have to make a circuit board. So I had to make this circuit board, this adapter that brings all this out so that it has a DIP-like package so that we could prototype and maybe put it in something like this and then run some wires to it and do some experiments. So let's take a look at that closely and see what that looks like. And this thing is just ridiculously small. And let's see if we can get it to focus for us. There we go. So this is super small. And I might be able to get it even closer if it'll cooperate. That's about the best we can do. And you can see those tiny little balls, those tiny little contact points. They are many times smaller than the tip of this pen. So under there, I believe this one probably has, I think, 20, 25 contacts that all had to match and mate with those little guys. So this is a sound processing IC. All right. So anyway, so that's digital. That's kind of what the ICs look like, and we're going to start putting things together with these kind of solderless breadboards, all right? And so that's kind of what's going to be going on. Okay, so that's it for this lecture, and so let's finish this one up, and I'll meet you in the next one, and we're going to talk about atomic theory and some of those subjects and keep going. All right, bye-bye. All right, welcome back to the next lecture. So we're going to continue our discussion of current, voltage, and a little bit of field theory. So now we're going to kind of move into atomic theory so we can start talking about charge and kind of the basis of electricity, which is important. And then we'll just go from here and see how far we get. All right, so again, you can look at a physics book, you can look at a college textbook on electrical engineering if you really want to dig real deep in this, but we do have to have some kind of knowledge of this, even if it's refresher, again, so that we have the same vocabulary and we're talking about the same things. All right, so so let's begin here. Okay, so the first thing is we're going to kind of be dealing with charge here. So electronics is, we want to move charge around, right? So we need to deal with electrons and holes, all right? So what we're going to do is we're going to talk about kind of what's referred to as the Bohr model, which is a very simplified model of atoms, all right? And in the Bohr model, we've got something that looks like this right here. And these days, this model's been kind of adapted and changed, and electrons are more of a probability function around the nucleus and that kind of stuff. But for the simple examples and the way that we need to do things, we're going to kind of pretend that this is what things are. So anyway, you've got a nucleus that has protons positively charged and neutrons, right? And then you've got electrons, which are the negative charge, orbiting around, right? So that's kind of what our model of matter is, right? Okay, and one thing is the protons are much larger mass than the electrons, all right, but they both have the same charge, okay? All right, now let's take a look at this, and if you haven't seen one of these in a while, the periodic table, and what's interesting is every time you look at this thing, and we're going to look at another one, but every time you look at this thing, there's more and more elements in here. So you've got to continually kind of update these. Anyway, so here's a periodic table. All right, and we're going to be talking about some materials here and some of their properties and kind of have this as a little bit of a reference, all right? Okay, so all this is going to be leading up to being able to understand semiconductors, all right? So, but to understand semiconductors, first we need to understand conductors and insulators and kind of what gives them that property. All right, so some of the common conductors that you're probably used to is copper, which is a Cu, silver, Ag, gold, Au, aluminum. All right, so everyone's kind of worked with these, and copper wire. Silver is very expensive, but it's a very good conductor. It's actually a better conductor than copper is. And gold, gold doesn't rust or tarnish, and so gold is used in electronics. It's a very good conductor. And actually, I believe that its conductivity is less than that of copper. So it's actually not, a lot of people believe that gold is a really, it's the best conductor. It's not the best conductor, but it has other properties. It doesn't rust, it doesn't tarnish, and those properties are more important than conductivity. And a difference of conductivity of gold and silver and copper is fairly small. All right, then we have aluminum, which is another good conductor and a cheap conductor. So for example, the wiring in your house, a lot of it is aluminum conductors because it's really cheap. Copper is very expensive, so a lot of times there'll be aluminum alloys instead of copper because it's a lower cost. All right, now what we are really interested in is the things called semiconductors, and semiconductors are going to be the basis of our diodes, our transistors, our field effect transistors, everything digital and analog that we kind of build that's based on semiconductors uses this technology, all right? So before we get into that, let's kind of remember some nomenclature here. And then of course carbon, which is a poor conductor, carbon. And carbon is actually used in resistor construction. So they use carbon because it's a poor conductor so it doesn't conduct very well. So if you want to make a resistor, that's something you would make a resistor out of, carbon. Okay, and again, all this stuff is kind of high school chemistry and physics. I'm sure if you look at it, kind of remember it. So we have the atomic number. All right, any given element has a number of protons, which is also referred to as the atomic number, and the atomic weight is the number of neutrons plus the number of protons. And actually, the weight is the number of neutrons plus protons plus the weight of the electrons. But the electrons are so small, their weight, that it's not going to have much of an effect if you want to do a calculation of number of neutrons or number of protons. So you kind of can use this equation to round it to the nearest integer, excuse me, and to compute these other values and just ignore the electrons. So anyway, but let's keep going here. Now, silicon, for example, has 14 neutrons. We go up here and we look at silicon. And if we look it up, silicon's over here, and here it is here. Let me zoom in a little bit. And we see that its atomic weight is 28. So 28, which is 14 neutrons, 14 protons, and then the weight of the electrons. That's what that kind of fractional part is right there. All right, so again, just some chemistry stuff, but we're going to need to know this. So let's just kind of keep going through it here and looking at it. All right. Now, if you look at the weight of a neutron, weight of a proton, they're slightly different in the third decimal place, but they're all 10 to the minus 27 kilograms, very, very small. Neutrons have no charge, protons have a charge of E plus, electrons E minus, and the charge is, remember the coulomb, right? So it's this many coulombs. So if you take the number of coulombs and divide 1 over that or find the inverse, that's the actual coulomb charge. So it's very small, 10 to the minus 19th coulombs. But the interesting thing is, they have such different mass, but yet their charge is the same. So that's interesting. And then, of course, a neutron has no charge. All right. So, okay, so now we've got our particles. So we know we're going to be moving electrons around. Now, a lot of times when people start with electronics, they think of, so you've got electrons, which are negative charge, and then protons, which are positive charge. So they think, are we moving protons around? No, we are not. So protons do not move around. So how do you get positive charge? Well, positive charge is the lack of negative charge. So, and we call those holes, all right? So we'll kind of get to that in a minute, all right? And let's take a look here. And yeah, so let's start talking about this. All right. So we've got conductors, insulators, and valence. So a conductor conducts because the outer shell of the atom, all right, which is called the valence shell. So the outer electron shell of the atom has loose electrons, or they're weakly bound. So they're very easy to move around. So they can move from one atom to another, or they can be completely ejected out of orbit fairly easily. So that's a conductor. An insulator is where the outer electrons are bound very tight. And so the outer electrons are paired usually, and that keeps them tight. Or there's nothing, or there's many electrons in the valence shell, which binds them tight as well. All right, so an insulator has very tight electrons in the outer shell, and a conductor has very loose electrons in the outer shell. That's all we really need to understand. All right, and then here we have kind of a depiction of copper and showing, electrons are moving. So basically, we've got these outer electrons in this outer valence shell, and they're just moving from one to another. And what's pushing them is a voltage. So this is the actual current, right? So the electrons are moving, that would be the current. And what's pushing them is a voltage or a potential field. That's what's pushing them, all right? Okay. Now, if you want to, another little thing is, so the way that these electrons fill up, they fill up in shells, and these shells are named S and P and D and F and so on. Now, what's kind of cool is, if you want to see how these shells kind of fill up, you can do this and learn to do this, but there's a lot of counterexamples. So if you go online, this is kind of a really cool p-table orbital. And what it does is, say if you select silicon here, and we select this, we can see how the orbitals actually fill up. So you can see this tiny little thing here, a little bit small on the screen, but you can see 1s, 2s, 3s, 2p, and these arrows, up and down arrows, those represent electrons. And each electron, this just represents its spin, which the electrons really don't spin, but we just call it spin. So there's up spin and down spin. And so you can see here, these outer two electrons, they've both got up spin, but they're not paired with anything in the silicon. All right, so silicon, for example, has this electronic configuration. All right, and so that can kind of help us figure out other things that we want to use with silicon to change its properties. All right, so we're going to get to that in a second. All right, so anyway, that's kind of how you deal with these orbitals and how they get filled up, and you can read how to do that. And then here's just some shell configurations, and basically you could just look at a periodic table and see these, but these kind of how they go, and you see there's method to the madness. So if you only have one electron like hydrogen, it's just 1s1. Then the helium, it's 1s2. And the S shell can only hold 2 electrons, so now we got to go up. So lithium has 3 electrons, now we need 1s2, 2s1, and so on and so forth. And you can kind of memorize some of these and then figure out how to write the rest of them. Again, we're really interested in things like silicon, carbon, copper. All right, now let's talk about this whole concept of holes and electron current and hole current. All right, so again, we're going to come back to voltage and fields and all that in a little while. But when we have a current, the current is ultimately being generated by an electric field. So in this depiction right here, we have an electric field, and the electric field is three-dimensional in space, of course, but we're showing it flat here. And here is the positive pole of the electric field, and here's the negative pole. So the field lines would be going from positive to negative. All right, in this case, the electrons here, so the electrons are going to want to move to the right. All right, so this is the positive side of things. So the electron, which is negatively charged, is going to want to move to the right. So here's a couple, say, conductors, conductor atoms. So what happens is these electrons, these atoms, these electrons are inside of this electric field. This is exciting the outer shell here, and it's causing these electrons to jump out of the shell, which they're very loose in the first place, and they jump over to the nearest atom in the direction of the electric field. And when they do that, there's a current flow. And once that electron comes into this atom, it doesn't like that, and it ejects the electron because it wants to get back to neutral charge. And so the electrons start moving to the right. Now, if you sit and take a snapshot of this over time, you're going to see electrons moving to the right, but at the same time, you're going to see lack of, or holes, the holes where the electrons were, they're going to be moving to the left. So almost you could think of this, say like you're in traffic, and the cars are moving forward, but as the cars actually move forward, every time a car moves forward, there's a hole it leaves. Then you fill up the hole with the next car, you're behind it. Then that hole just moved in the opposite direction, and that fills up. And so the holes or the spaces move in the opposite direction. So this is really fascinating. If you look at traffic from an aerial view, you see the traffic flowing forward, and then you see the spaces flowing backwards. And it's the same thing here. So we call the spaces holes. So we've got electrons and holes. Now, when we are talking about electrical engineering and electronics, there's two kinds of current that people like to talk about. So when I went to school, we used electron current. So we like to talk in terms of electrons. All right, so pretty much until, I don't know, maybe the 90s, 80s, 90s, everything, people like to talk about electron current. Now I would say that most colleges use conventional current, which is hole current. So it's the same thing, but instead of fixing our eyes and our focus on the electrons moving, we focus on the holes moving in the opposite direction. There's no difference. It's just a sign convention, so you got to pay attention to pluses and minuses, and then you have to realize you're talking about holes and not actual electrons. So if something has to do with the actual particle, the charge, then you need to think about electrons. So keep that in mind. Current is electron current. It's always actual electrons, but we can talk about this thing called hole current, which is the lack of electrons or the holes left by them as they move, and we call that conventional current. All right, so we call that conventional current, and we call the electron current electron current. All right, so we're going to be using conventional current in all of our stuff. All right, so let's keep going here. Let's see what else here. All right, now this is another depiction here. Let me zoom in a little bit for you here. And again, we just want to really kind of make this clear. So we've got, here's an insulator, say, and here's another insulator. This might be a cross section of a piece of wire. So we're looking at a piece of wire cross sectionally, and so we've got this electric field, and from plus to minus, and that electric field really is it's a voltage. And so now we see the current, we see the electrons moving in this direction, and now we see the holes moving in the other direction. And so we've abstracted these particles moving, and now we're kind of calling the positive charge, which is not really a positive charge, it's a lack of a negative charge. We're just calling those E pluses, and we're calling the actual electrons E minuses. And now we can think of, so there the electrons move right, and the holes move to the left. So this is a fine convention, works great, no problem, as long as you're consistent, all right? So that's what's really kind of going on inside of the wire, all right? Okay, so again, it's electron current and conventional current. Okay, so now let's get into current and voltage here. And I think this is a good place to stop right now because we've kind of talked a little bit about the atomic theory. And then the current and voltage is kind of a big subject in itself. There's one thing I want to show you before we go, and let's go back to this periodic table. And that is, again, if you can, it's ptable.com/hash orbital. And there's countless periodic tables on here. But what we're going to really focus on is the silicon, the boron, and phosphorus for creating semiconductors. If we come back, and let me come back to this for a second, because we're not going to get back into this material for a while. And okay, I wanted to show you this before we stop. Come back to this. So we have silicon here, which is called a semiconductor. And like I said, we're going to have a whole section on this, but I just want to kind of talk about this for a minute. So silicon is a semiconductor. And so that means it's a poor conductor and it's a poor insulator. So it's not really good at either. But we can make it really good at one or the other by doping it. And what doping means is we're going to introduce another atom into the crystalline matrix, and we're going to change the bulk properties of the material and the electronic configuration. So silicon is it has 4 electrons in the valence shell. And so when it's neutral, it has 4 electrons in the valence shell. Boron, on the other hand, this has 3 electrons in the valence shell. All right, and then phosphorus, which is a pentavalent. Okay, so boron is trivalent, it's called, and phosphorus is pentavalent. This has 5 electrons in the valence shell when it's neutral. So when these 3 atoms are neutral, they have 4 electrons in the valence shell. Boron has 3. And phosphorus has 5. So if we were to take phosphorus or boron and we were to add it into a silicon, all right, and this is how semiconductors are made. If we were to add it into it, so like let's go down here and take a look at this. All right, so here's this is copper atoms, but let's just pretend this was silicon. So this is all silicon, let's say, and let's say it's all neutrally charged. So right now it's neutral, it's at equilibrium, there's no net charge. If we start putting phosphorus atoms ever so often, what we do is we change what the net charge is inside of here, and we change the bulk properties of it. That's exactly how a semiconductor is made. So if we add phosphorus, we're going to add more electrons, and this thing is going to become overall negatively charged, or we're going to end up creating an N-type semiconductor. By the same token, if we add boron, we're going to add something that has 3 electrons, 1 less electron than silicon, so it's slightly positive relative to the silicon. But in bulk, it's going to seem like a net positive charge. So that's how we create a P-type material. An N-type and P-type, we're going to figure that out more. But anyway, the whole point is you literally just have the atoms in a crystal matrix, and you add in every now and then either phosphorus or boron, and that's kind of how you make a semiconductor. And you might be saying, well, how do you add things into atoms? Well, what we do is we take silicon, pure silicon, and then we take a gas of phosphorus or boron, and then we heat that gas up to a very high temperature, and then that gas will slowly diffuse into the silicon. And based on the pressure and the temperature, there are equations that dictate how much diffusion and concentrations of that actual diffusion, and then we can kind of tune the doping, as it's called, to what we want to get the properties that we want. All right. So anyway, just put that in your head. So when we get to semiconductors a little bit more, we will kind of know what we're talking about a little bit. So let's get back here to current and voltage. So like I said, we're going to leave off for right here. This is a good spot. And then we're going to jump into this. And this is now, we've kind of got all the things that we needed to figure out. We've got our units. We've got a little bit of atomic theory, a little bit of chemistry refresher about atoms, this and that. And so we've been talking about current and voltage, kind of hand waving. And we don't really know exactly what it is, and now we're going to figure that out, and then we're going to be able to start getting more into actual use of electronics and using these things. So anyway, I'll see you in the next lecture, and we're going to talk about this, and we're going to move forward. All right, so finish up, and I'll see you then. Bye. All right, welcome to the next lecture. So we're going to continue moving through this material, and we're going to talk about current and voltage. So last time we did a little bit of atomic theory and kind of looked at conductors and insulators a little bit, talked a little bit about semiconductors. And again, we're going to revisit things many, many times so that, we really understand them and kind of, don't have to think too hard to remember things. So again, it's about repetition when doing electronics. All right, so what we're going to do in this lecture is we're going to talk primarily about current and voltage. We're going to do a little bit of hands-on stuff, and we're just going to see how far we get in this lecture and find a good place to stop when we've got enough information. All right. So let's begin here. So current and voltage. All right. We've talked about both these a little bit, but we're still not quite sure exactly what they are. I think we've got a little bit better handle on what current is, but voltage is a little bit more difficult. So let's start going through this and see what we can figure out here. All right, so let's actually read this definition. Referring to the figure below, figure 1.9, which we'll take a look at in a second here, the amount of charge Q, which are electrons, that passes point P as a function of time defines current. All right, or mathematically, current is equal to the amount of charge per unit time passing a point. So in this case right here, we have this vertical barrier, and we're looking at a two-dimensional space. And we have charge here, these electrons, which are moving to the right, and they're moving past this point. And as they move past this point, we have this charge, which we're going to call delta Q. So some charge is moved through a point, and that we're calling that charge delta Q. And the amount of time that this is taken is delta T. All right. So this is the actual basis of the definition of current. All right. And so all we really care about is there's some charge that's moving through a conductor or whatever, moving past the point, and that charge delta Q, and it takes delta T time or some small amount of time. All right. And the definition here is current I, which we usually call it I, is dq dt. All right, and all that means is dq dt is simply a small infinitesimal amount of charge and a small infinitesimal amount of time. All right, so dq dt. It's just calculus kind of terminology, but you don't need to know calculus. It's just delta Q, delta T. All right, so we're going to move charge through a conductor or something, and some amount of time that this occurs in, this charge motion or this mass movement, and that's current. That's all current is, all right? So it's just charge per unit time. Okay, so we talked about what a coulomb was before, a coulomb of charge, and that's just a number of electrons, right? And so if we move that large number of electrons, a coulomb, and we move that much charge past a point in 1 second, all right, so 1 coulomb per second, this is what we call 1 ampere. So 1 amp is 1 coulomb of charge move through a point in 1 second. All right, and that's an ampere, and it's as simple as that. So that's an amp, and that's quite a bit of current. So to give you an idea, how much current can like kill a person, a tenth of an ampere can kill a person. So an amp is actually quite a bit of current. All right. So and then we'll continue again talking about conventional current and which are positive holes, right? The lack of electrons or holes. And we're going to deal with conventional current, which is not the electrons moving, but the holes moving in the opposite direction. All right. So kind of looking down here, we've got kind of one of our first little actual circuits we're going to look at. All right. And what I want to bring your attention to here is, so we've got a plus here and we've got a minus here. Now these represent not electric fields, but actual voltages. So this plus and minus, this is a voltage. So this is like, V plus, and this is kind of like a V minus. And the same thing here, this is like a V plus, and this is like a V minus. All right, so all we need to know right now is this voltage is higher than this voltage is higher than this voltage. So conventional current, which are positive virtual charges, or we're going to call them holes, so nothing's actually moving. The electrons are moving in the opposite direction, but the holes are moving in from positive to negative. So in this depiction right here, the top depiction, this is saying that we've got a voltage here, and this is going to induce a current, and that's kind of the way that we want to say that. It's going to induce a current. We have this symbol here as a resistor. All right, and again, we haven't learned these, but we're going to learn them a little bit later. So there's a lot of chicken and the egg stuff with electronics. You got to show something to kind of use it before you even learn it. All right, and I'm saying here that there's plus 5 amps of current flowing in this direction. So whatever this resistor is and whatever this voltage is inducing a 5 amp current in this direction. So now here's the important part. This 5 amps is conventional current. All right, so we have 5 amps of conventional current. And then if we wanted to say what's the current moving in this direction, we can put an arrow there and say, hey, current's moving in that direction. But that would be minus 5 amps of current moving in that direction. And that way the signs are consistent. So you could use this version here, or you could flip it to this version here, because now the signs are consistent. So the current's moving in this direction, but it's a negative current. All right, so it's equivalent. All right, so as you're doing circuit analysis, ideally, if you can make things positive, it makes them a little bit easier. So if you can have the arrow moving from plus to minus and it's a positive current, that's better than a negative current moving from negative to positive. Just makes it easier sometimes just to think of things. Okay, all right, so that's current. All right, so that's kind of some current flow, and what's inducing this current is a voltage. All right. Now let's talk about some scale of things, just so you get a feel of current. Because this is not something that you use every day, and it's like you're not going to have a good frame of measurement. Like if someone says, how tall is a person? You're like, most people are 5-6 feet tall. But when it comes to current, you have no frame of reference. So let's look at some of these values here. So a single gate in a microprocessor or a microcontroller might be 10 nanoamperes of current. That's how much current it might use, or might be able to support or sink or source, or less, maybe 1 nanoampere, or maybe it's 1 picoampere. Okay, so we're talking about a very small amount of current is required in a modern processor for a gate. A light emitting diode, and we're going to actually do a little experiment here to kind of see this in a little bit. A light emitting diode actually uses quite a bit of current, and most LEDs, most little lights, LEDs, and so let me quickly show you one here. Let me grab one, and we're going to play with these in a little while. But here's one here. So that's a red one, obviously. Here's a green one, and then here is a clear one. And this one's actually, I believe it's a bicolor. We're going to find out. So this is actually red and green, I believe. And so depending on which way you apply a voltage, it'll be either red or green. So those are, 3 LEDs, okay? So these use a lot of current. And 10 to 20 milliamperes usually for those kind of LEDs, and then bright LEDs that you might see in flashlights, those could actually take amps or hundreds of milliamps. But when we're talking about those small LEDs, about 10, 20 milliamperes usually. All right, a digital TTL chip, we don't know what TTL means, but it means transistor logic. It means gates composed of transistors. And there used to be diode couple logic and resistor transistor logic. And so these days, most gates are CMOS gates, but TTL is still around, and it's kind of a good frame of reference if you want to do kind of 5-volt stuff with, say an Arduino is a 5-volt device, the Arduino Uno. Anyway, digital TTL chip, the chip might use, 20, 30, 40, 50 milliamps when it's driving or syncing. In other words, those gates can usually output 5 to 20 milliamps. So not a lot of current, but in the milliampere range. And then a single gate in the TTL chip, maybe that's going to use about 5 milliamps, maybe it'll use 10 milliamps when it can drive. So it's driving and sourcing and syncing current. That's what we're talking about. When it's just sitting and not doing anything, that's called quiescent current, and that's always going to be much, much less. So the quiescent current will be in hundreds of microamperes or even much less. And if it's CMOS, it'll be much, much less. All right, but again, we're just trying to get an idea. LCD calculator. So like for example, here's a calculator that has an LCD. And so this is actually something I wanted to comment about. This is a TI 83 Plus, and a lot of engineering students have these TI calculators. This has a Motorola 68000 in it, which is pretty cool. So this is a pretty awesome calculator that you can do engineering on and whatnot. And I recommend that you have one with you. And then here's a little $15, I think this is a Casio, Casio scientific calculator. Get one of these and have it with you. Because when we're doing these things, you can just sit here and type something in on the calculator and get an answer, rather than use an online tool like the built-in calculator, even a scientific calculator. It's just kind of a pain doing it on the computer. So I recommend you have a calculator with you so you can kind of bang things out and figure things out really quickly. So anyway, the LCD calculator, maybe it's 50 milliamperes. And that's going to be because there's a microcontroller, a microprocessor, it's got a display, it's got a lot of other things going on. And that's, the current that this thing is going to be drawing as it's operating. All right. And again, just ranges. There's extremes in both cases. A 27-inch, 35-inch TV set, maybe these things are going to pull 2 amps of current. Right, and then again, depending what technology it is it an old CRT? Is it LCD? Is it plasma? Is it LED, OLED? And these amounts of current will change, but you're talking about amps, right? A personal computer, this could be many amps, right? So 5 amps, 10 amps, and so forth. So for example, and then this is why we like our calculator. I have a 1200. Actually, no, I think this one's a. No, it's 1,000. So this is a 1,000-watt power supply, and the AC power coming in is 120 volts root mean square, and we're going to talk about what that means in a second. Power is voltage times current, and we're going to learn that also in a minute. Power is voltage times current. So I've got 1,000 watts divided by the voltage, which is 120 volts, and that's 8.3 amps. So my particular computer pulls at least 8.3 amps with that power supply, and probably pulls a lot more because it's inefficient and all that. All right, so anyway, personal computers, you're talking 5 to 10 amps usually. A hair dryer, this is going to pull a lot of current. All a hair dryer is basically a motor and a heating element. And this will pull almost the maximum current you can pull out of a socket. So in the United States, if you're watching this from another country, most sockets support anywhere from 10 to 20 amps, most AC sockets. And a typical hair dryer is about 1,000 watt, 1,200 watt is pushing it because it gets really hot. And so if you take that 10 amps, right, take 10 amps, and if we take 10, so power is voltage times current, we take 10 times 120 volts, root mean square in the United States, 120 volts, we're going to get 1,200 watts, right? And so that's kind of how you compute that. So that just gives you an idea. So I want you to have a feel for these different currents and the values of these currents for different things. So you just kind of have an idea of what you're going to need for different components and as you construct things. Okay. All right, so now let's talk a little bit about voltage here. All right, so voltage is a little bit tricky, so let's just look at some examples and we'll kind of get through this. All right, so let's say that we have two parallel plates, and say these plates have charge. So there's a plate and there's a plate. One plate has positive charge and the other plate has negative charge. All right, and between them could be space, air, something else. This is actually a capacitor. But for now, we're just using it as an experiment because we want to create an electric field. And so when we have all these plus charges and we have these minus charges, somehow we got them on there. And there's going to be field lines going from all these pluses to the minuses, all right? And this is going to create this electric field, all right? And so we've got an electric field, and then we have charge in this electric field. So we've got this electron right here, all right? And we have a hole here, but let's forget about that. So we have this electron here, and when we put this electron inside of this electric field, there's going to be a force exerted on it. So the electron has mass, and there's going to be a force exerted on this electron. And this force is going to have something to do with this electric field. And this electron is going to move in this electric field. The electric field, of course, is a three-dimensional field, and we're just showing a two-dimensional flat depiction of it. So first thing that we need to create as a fundamental idea here is when you put charge in an electric field, there will be a force exerted on the charge, right? So that's number one. So we can move the charge. That's key. So now we know that current is charge moving, all right? But somehow we got to move it. And so voltage is this thing that's going to ultimately be the thing that helps us move the charge. That's the pressure, and it's derived from the electric field. So let's keep looking here and see what we get. So, all right. So we've got a charge, we put it in an electric field, a force is exerted on it, all right? And if we call that charge, let's just call that charge little q naught here, all right? Now, this is an important point right here. And so so we're going to change the charge as potential energy by its motion. In other words, we place the charge in one place, and that charge we're going to call this q naught, little q naught. And if we move it from one place to another, at one point it had some potential energy, and at another point it has a different potential energy. And remember, there's different kinds of energies, right? There's kinetic energy, which is the energy things have because of their motion. Potential energy is the energy things have because of their position, all right? So for example, if I raise this up here, this has gravitational potential energy because I can drop it, right? And now, this energy, this potential energy is going to be turned into kinetic energy, right? So it's the same thing with the charger. So all we really care about is we have charge, little q naught, we put it in this electric field, and if we move it from one position to another, we're changing the amount of potential energy. Energy is changing. That's the takeaway here. Okay. All right. So, all right, let's keep going. All right. Now, this next drawing here now is kind of really uncovering what's going on here. So again, we've got our electric field, we've got our charge right here, and we're calling that Q naught, and we've got a point A at XYZ, and we've got another point B, which has got XYZ coordinates. Again, we're looking at three-dimensional space in reality, but in this picture, just two-dimensional. The electric field is also a three-dimensional vector field, but we're just assuming it's going straight down here in this depiction. If I move this charge, and here's the key, if I move this charge from this point to this point, right, so we have to work to do this, all right? So voltage is the potential energy per unit charge. Voltage is the potential energy per unit charge, all right? So just let that sink in for a minute. The change in potential, right, so dV, so the change in potential equals the change in potential energy, so the change in this voltage, right, so the change in voltage, voltage V, change in voltage, is the change in potential energy per unit charge, okay? So now let's go a little bit farther, and then here's where it's going to kind of come together here. Let's erase that. Okay, so potential energy is energy. We measure energy in joules. All right, charge is measured in coulombs. All right, our Q0, that's charge. All right, and here's the final definition. So 1 volt equals 1 joule per 1 coulomb. So 1 volt equals 1 joule per 1 coulomb. So this is, you just got to kind of think about this. So what that means is that 1 joule of energy, if 1 joule of energy is used to move 1 coulomb of charge through a potential difference or voltage of 1 volt, all right? So again, 1 joule of energy must be used to move 1 coulomb of charge through a potential difference or voltage of 1 volt. That is what 1 volt is. So backwards, it's 1 joule. So you move 1 coulomb and you expend 1 joule of energy. That's 1 volt of potential difference. That's it. So that's what voltage is, all right? So now you can go back and you can kind of look at a physics book and you can look at this more in depth and look at YouTube videos, but that's all we really need to know. So at this point, we're going to kind of make this model where voltage is a pressure. It has something to do with energy and it has something to do with charge. All right, and moving the charge through space, energy is exerted or required to do that. All right, and 1 joule is used moving 1 coulomb. That would be a 1 volt potential field. All right, so let's move on to now generating voltage now. Okay, so let's continue on with how we're going to generate voltage. All right, so the simplest way to create a voltage is to use a battery. All right, so batteries we're all familiar with. Also, magnetic fields can be used to generate a voltage, and also the photoelectric effect. All right, so let's start and let's talk about batteries a little bit. All right, so everyone has played with batteries. And batteries are, there's a chemical process inside, and we're not going to get into this too much. You can read through the notes if you want to know a little bit more, read something on batteries in particular. But the bottom line is there's 2 kinds of batteries, primary batteries or primary cells, which are not rechargeable, and then rechargeable batteries. And there are countless different kinds of battery chemistry, and that just simply means the chemicals that are used inside of the battery to generate the chemical reaction that creates a voltage difference. So lots of things will create a voltage difference. Dissimilar metals will. You can make a battery out of copper and lemon juice, all kinds of things. So batteries are really interesting, and they're actually pretty easy to make. So, but most of the batteries that we're used to are kind of these standard consumer batteries and maybe car batteries. All right, and let's go and take a look. Kind of come back here, come over here. All right, so if we look at the battery, typically the top kind of has a little button, and that's the positive, and the bottom, which is flat, is the negative for a cylindrical cell, and this is called a cylindrical cell. Prismatic cells would be things that look like rectangular solids. I'm going to show you some of those in a second. All right, so just some nomenclature. So the positive part of the battery is the anode, and the negative part is the cathode. And here's the symbol that you'll typically see when batteries are drawn on schematics. So we can generate a voltage with batteries. All right, so let's take a look at a couple batteries, and let's actually measure the voltage. Let's do some hands-on stuff. We've been doing a lot of theory for a while, so let's see what we got. Okay, so what I want to do here is just put a number of batteries out here so you can kind of take a look at what we have here. And we will kind of go through these, and there's no advertising here whatsoever. These are just random batteries that I have. But I'm going to show you there are many different kinds and sizes, which are very surprising once you get into it. So he doesn't want to stand up there. All right, so the first one, so here we go, which is kind of, let's just do this, kind of lay these out here, move some of this away. So over here we have AA cells. These are AA, and for example, this one right here, this is a primary AA cell. It's a Duracell Quantum, and if you read on it, there's some information that most batteries have. So here's, it says here's the plus side, and of course that would be the minus. And then it says what the voltage would be, and this is typically the unloaded voltage. All right, and let's zoom in a little bit. and that's typically the unloaded voltage. So the second that you put a load on here, the battery voltage is going to drop down a little bit. And the reason for that is that internally in these batteries, they aren't perfect. They have internal resistance, and because of that resistance, some of the voltage will drop over the internal resistor. All right, so that's that guy right there. And then here's a rechargeable battery. And then if we look on here, and you know what? Let's go into the zoomed camera here, so we can see a little bit better. All right. So if you see here, this is rechargeable. It's a AA, 1.2 volts and 2400 milliamp hours, and it's nickel metal hydride. And so the 2400 milliamp hours, that's a measure of kind of the amount of energy stored in here, how much work this thing can do. So what it means is that this can supply 2400 milliamps, all right, for 1 hour. So 2400 milliamps for 1 hour. Now it can't actually supply 2400 milliamps for 1 hour. If you try to do that, it wouldn't be able to do it. But you could probably do, so if you divide that 2400 by 10, 240 milliamps, so 240 milliamps for 10 hours. So it's kind of a generalized number that has something to do with how much energy is stored, but it's not really a good measure. But it's what they have on most batteries. What they really need are watt hours, because watt is actual power, and milliamperes is talking about just the current, but it's not talking about the voltage, and the voltage could be dropping dramatically as you're pulling power from this. Anyway, so this is one kind of chemistry, nickel metal hydride 1.2. So it's way less than 1.5. So some devices won't like that. All right. Okay. And then let's see here. You know, there's just another AA. This one says 2800. And of course, you definitely want to check these things out. So when you buy batteries, you want to verify that they do what they say they're going to do. So you can kind of measure their power, their depletion, their charge rate. So anyway, there's another rechargeable battery. All right, let's see here. This one is interesting. So this is a AAA battery, right? And this is another rechargeable. This is Tenergy, which they make a lot of lithium-ion batteries. So this is still nickel metal hydride. Let's take a quick look over here. All right, nickel metal hydride. And again, you kind of scroll around, look around, and you can see, you know, AAA 800 milliamp hours. So the voltage is the same, but this has much less overall energy storage. And of course it does, because its volume is less. So the amount of energy you can store in these batteries is directly proportional to their volume, and also related to their chemistry. Okay. All right. Now we've got this kind of heavy-duty Rayovac battery. This is not even an alkaline. This is another primary cell. All right. And again, take it over here and we'll kind of take a look and look for any information. So again, it says 1.5 volts, and this is a D-size cell. And then between the, so a little smaller than a D, of course, is a C-size cell, which I don't have any on here on hand right now. Now here's one that you may have not seen. Most people have not seen this. So here's a AAA in my left hand, but in my right hand is a quadruple A. So that's kind of interesting, a quadruple A battery. So let's take a look zoomed. And so there's the AAA in my left hand, and then here's a quadruple A. So you can kind of see they've got different diameter, and their lengths are actually different as well. Again, this is a primary cell in this example, and this one's alkaline. And of course, if you look on it closely, you should be able to find it's this particular one is also 1.5 volts, so 1.5. And then another interesting thing, instead of calling it a quadruple A, it has different names that people will use. That's more of the battery name, so E96 or LR61. All right. So anyway, that's the really small battery, quadruple A. All right. Okay. Now, another battery that everyone's used to seeing and putting in their different products and consumer products is the 9-volt battery. So here's a 9-volt battery, and this is a energizer. And so this is a prismatic cell, so it's rectangular, right? And so this has got kind of interesting leads on it right there and right there. And of course they go to, your little snap connectors, which, everyone's snapped one of these things in. So, just one of these connectors right here, and they snap in. And so a lot of times it's kind of hard to remember which one is negative and positive. But the big one, the big one is the negative, excuse me, the big one is negative and the small contact is positive. So anyway, we put those on there, click that down, get a really good contact, and then we have these two leads which we could then plug into some circuit or something if we wanted to use the 9 volts. So now if we take this over, and so this is on here really, really good, and we don't want to damage it. So let's get a tool. So, again, you want to have lots of tools available to do things. So I just kind of brought that out. And you'll see, for example, here, which is kind of off screen, but I have just some needle nose pliers right here. So those are just needle nose. I've got some cutters, all right, some diagonal cutters so I can cut things. And then here are just some wire cutters and strippers, all right. So always good to have tools around so you can kind of work with things and not damage them. All right, so let's take a close look at this 9 volt over here. And 9 volt, this is alkaline. That's saying its expiration date 12 of 2021. Good luck with that. And let's see if there's any other useful information, just warnings, and that's about it. Now, the interesting thing about the 9 volt batteries, if you rip one of these apart, actually inside of here are 6 cells. And the 6 cells are kind of this quadruple A battery size. So you see 1, 2, 3, 4, 5, 6. And what's 6 times 1.5? It would be 9. So that's how they generate the voltage for the 9 volts. So it's actually 6 of these in series, 6 of these quadruple A, not actual quadruple A's, but the same size. All right. So that's that. So those are those batteries. Now, a couple other interesting batteries that are not so common. Let me show you these. I have at least one of them here that I want to show you. Is this one right here. And this is an A27. There's all kinds of batteries. If you go on Wikipedia and look up battery types, there's many, many batteries. And so this one, what's interesting about this is 12 volts. So it's a 12 volt cell, and all of these normal cylindrical cells are all 1.5, no matter what size, are all 1.5. And this one is 12 volts. So so it has very little current. So this battery can drive very little current, but it's at 12 volts. So this is used in devices that need a higher voltage but don't care so much about the current. So again, many, many different kinds of batteries. All right, one thing real quick, let's just for fun, let's grab our meter here. So we're going to grab our meter, and let's we'll put it right. First, let me show you here. Again, we want to always kind of do as much as we can every time and kind of show different things. All right, so here's our meter, and again, we're going to go over equipment in a little while, many different pieces of equipment, but we're going to put it on a voltage, and we're going to put it on DC, the auto scale, and right now it's saying millivolts because it's on auto, and it's going to auto range to the range that we want. And then these leads are down here in common and voltage. If we're going to measure current, we'd have to pick up this red one and put it here, and higher current we would put it here, but we'll get to that. All right, so we've got our leads, and then all we're going to do is we're going to put it on these batteries, and we're going to measure what their voltages are real quick. Okay, so this is a heavy-duty D-size cell. It should be 1.5 volts, and we put it on there, and it says 1.625 volts. What's going on there? Well, again, these batteries have varying chemistries, so this one is simply 1.625, and under load it will probably drop down to 1.5. All right, so that's good. We like that. It's higher. All right, here's our primary cell from Duracell. It's Duracell Quantum, and it's got one of these little battery checkers. If you hold it down, and I'm holding it down, and nothing is happening, so this one might even be dead. All right, so let's check this. And we look at it, and it says 1.536 volts. Now, even though that voltage shows there, this battery might be fairly depleted. So if we try to actually use it and draw current from it, it may not be able to supply any current. So even if the voltage is there, it may be nearly dead. All right, so that's another little interesting thing. So 1.5 volts. And then now, Here is a rechargeable battery, the nickel metal hydride, and this is supposed to be about 1.2 volts. So we put it on there and it's 1.4. So that's a really good battery, 1.4. And here's another vendor, this EBL, and we put it on there and we get 1.34. Now, one thing, what if I switch these two leads? What's going to happen? So we switch these two leads. So this is the negative side and this is the positive side. So now I'm putting positive to negative and negative to positive. Is something bad going to happen? Let's find out. So nothing bad happens, but you see the negative sign in front of the number on the meter? That's all that happens. And you're measuring a negative voltage. Now we're measuring a positive voltage, okay? Just exactly what we would expect, okay? Here's the quadruple A, the little tiny quadruple A. So let's check this out. And that's 1.455, cool. And okay, let's go to our 9 volts here. So we've got 3 different types of 9 volts. So we've got one 9 volt that's this is a alkaline battery energizer, and then we've got a Chinese brand, Go Light, which is probably out of a remote control from something that I got, a TV or something that came with it. And then here's an Eveready, but this is a heavy duty. This is not alkaline. Okay, so let's take a look at these. Okay, so here's the energizer right here. So let's see what this is. So we put it on there, and we got 9.39. All right, so that's good. And then we do the let's turn them all the same way. Then we'll do the Eveready heavy duty. So Eveready heavy duty. Put it in there again, and it says 44 millivolts. So this is absolutely dead. No matter what I do, it's dead. Now, an old trick that you can do is if you want to check a 9 volt battery, if you've got the guts, you can take this battery and touch it to your tongue. Touch it to the, not the tip of your tongue because that'll hurt, but the middle of your tongue, and you'll feel a little bit of current running through your tongue. And then as you gain experience, you can kind of tell how charged the battery is. So, anyway, so if I take this battery right now and I touch it to my tongue and I'm going to do it, it's completely dead. All right, if I take this battery right here and I touch it to my tongue, I can definitely feel that. You just go tap, tap, tap on your tongue. All right, let's look at this last one, the Go Light. All right, let's put our probes in the right direction. And 9.83. Okay, so all of those are doing what they should do. And then let's go back to this guy again, right? So this guy was 1.6. Now let's measure current. So to measure current, we have to put the meter in the circuit. And we're going to learn more about that, but just for fun right now, let's really quick do this. So the first thing we have to do is put this into current mode. So we're going to take the probe out. We're going to put the meter into current mode. We'll put it on milliamperes first, right? We think that this battery can supply milliamperes. All right, let's find out. Now, when we have the battery, so we've got this battery, which is this voltage source, it's got an internal impedance or an internal resistor. All right, so what the battery really looks like, let's go back and take a look on the screen here. So what the battery really looks like is this here. So let's draw it. So we've got our voltage source, our battery, okay, and that's one cell, all right. And this is the plus side, and this is the minus side. So this is kind of, what our battery kind of is symbolized by. And then, this is kind of in this thing, right? It's like a battery. And then on top, we've got this little top here, right? And so that's plus and that's minus. And this could be our, our AA battery, our AAA battery, our C battery, our D battery, etc. But this isn't really what's inside of the battery. This would be a completely idealized version of it. What's really inside of the battery, so this goes down here and makes contact with this bottom. What's really inside of this battery, there's an internal resistance here. All right, so we'll call this, RB for our battery. So we've got an ideal battery or ideal chemical source here, a voltage source. Then we've got a small resistor. So what's going to happen is this. When we take the meter, first, when we take the meter and we plug this into the meter, into the voltage meter, right, that we just did, and put our little probes there and we measure voltage here, right? We measure voltage. This is unloaded, meaning there's very little current, and we're going to look at this very specifically very soon. Very little current I that's very, very small that has to flow through this meter to measure the voltage. Okay, because of that, very little voltage is going to drop over this resistor. Teeny tiny little voltage will drop over that resistor. So we're going to see mostly the voltage over the voltage from the voltage source, or the just the chemical part here of the battery generating the voltage. But as we draw a lot of current through this, and we're going to learn the equations that govern this, some of that voltage will drop over this internal resistance of the battery. So now this 1.5 volt battery, as we draw a lot of current from the outside here, right, we'll only see maybe 1.2 volts, or maybe we'll see 1.0 volts, because so much voltage will drop over the internal resistance because we're drawing so much current. All right, so what we're going to do right now is we're going to make a circuit that looks very much like this, except instead of voltage, we are going to measure current, I. And we're going to do this exact same circuit. So now, if we were to do this to a perfect battery, an infinite amount of current would flow, because these are perfect conductors with no resistance. But these conductors actually have resistance, but very small. But this resistor, this internal impedance or resistor of this battery, is going to limit the amount of current. All right, but so we're going to find out right now by hooking up the meter to this circuit, and we're going to see what happens. So real quick, what we're really doing is this. So we have our battery here, and this is plus and this is minus. Then we've got a resistor here, which we're calling this RB. And then here's the circuit normally. All right, and then current would flow from positive to negative, right? So conventional current's going to flow out of here through this resistor, and we're going to learn about this very shortly, exactly what governs this. And this is a circuit that's going on right now. When we measure the voltage of this, what we're doing is this. We're going right here, and we were hooking this up to our voltmeter. Okay, so right here, we're hooking this up to our voltmeter, right, and voltmeter, and measuring it, all right, and figuring out what that is. So we just kind of hook that up in an open circuit, right, and there's a little bit of current that flows through here, and that's how the voltmeter works. All right, now what we're going to do is instead we are going to hook it up in the exact same way, but we're going to put the meter in amp mode, all right, and we're going to put it in series like this, and we're going to read what the current is, what the current I is, right, and what's going to happen here is this battery is going to push out a lot of current. It's going to go through the meter is going to measure it, and it's going to come back. But what's going to happen is whatever that current is, let's call it I, it is going to cause a voltage drop over this resistor. So this battery right here, let's say this is 1.5 volts, like up above. And if we pull out 1 amp of current, all right, and let's say that this internal resistance is just 1 ohm. And again, we don't know why this is true, but we're going to learn in just a second. So if we pulled out 1 amp of current and this resistor is 1 ohm, then 1 volt would drop over this resistor. So 1 volt would drop. So we would see here actually only 0.5 volts. We would see the 1 amp of current, but only 0.5 volts. So if we took another meter, so if we hooked up this meter here and drove this circuit this hard, and then hook up another voltmeter, all right, and we measured voltage V, voltmeter, like this. So now the voltmeter would have very little effect. It would just kind of be reading what's going on in the circuit, but we would see that at this node right here, only 0.5 volts is left, because we're going to drop 1 volt over this resistor if we have this 1 ohm internal impedance. So anyway, we can figure out kind of all this stuff, but this is really the model that's going on. All right, so let's go back and let's measure one more thing here. Okay, so we're back here, and this is going to be fun. All right, so we got the meter. It's on current mode. It's in milliampere range, and I'm going to tell you this thing's going to pull way more than milliamperes, but let's give it a try, and let's see what happens. So we put it on here, and it says 0L, which means it's out of range. All right, so now we're going to switch it to amps. We're going to put the red probe inside of the amp socket, and we've got our common ground where it needs to go, and now we're going to measure it again. All right, here we go. and we've got 5 amps. But notice how it's slowly dropping. Why is it dropping? Because the internal impedance is dropping a voltage, and what's happening is it's getting hotter and hotter, and as it gets hotter, less and less current can flow. So if I were to feel this right now, all right, it's starting to warm up. Okay, so anyway, in each one of these will only flow so much current. So we take the Energizer, we put it in there, 6 amps, but just for a few seconds. If we put the little guy in here, this double A, let's put this double A right here, 11 amps for a few seconds. Wow, I'm pretty impressed with that. If we take this teeny tiny quadruple A and do it, oops, 3.2, 3.1, but only for a few seconds, then it drops down. So these batteries can supply a lot of current for short amounts of time. So that's why you want to be careful how much current you drag from them. Okay, all right. So let's move on here a little bit and see what else we got. All right, welcome back. We're going to continue on with the material that we were just reviewing on batteries. All right, so let's see here. So what's next? So we've kind of looked at some batteries. We checked their voltages. We saw how much current they can supply, like the D cell, and surprisingly, that AA put out a lot of current. That nickel metal hydride battery, that surprised me. So, so now let's talk a little bit more about configurations of batteries and kind of how we can put them together. And typically we're not, you'll make battery operated devices, obviously, when you're doing electronics, but you'll also have things that have power supplies, which will take, say, AC to DC. So, a wall adapter to DC to a to regulation to a power supply and so forth. So that's not a battery system. So we're going to, look at those things too. But let's look at how these things, again, details matter, and it's super important that we understand all the little details so that we're not like, I don't know what's going to happen. So let's keep going here. All right, so increasing the voltage series cells and increasing the current parallel cells. All right, so let's take a look at this figure right here. So this is important. All right, so imagine if we have, 4 batteries here, and we put these 4 batteries in series. And again, there's some laws we don't know about yet, but we will. But let's just use kind of common sense here. So we've got these 4 batteries, and we put them in series. And you can think each one of these is like a pressure behind the previous one, behind the previous one, behind the previous one. So the voltages actually add up. All right, so if you've got 4 batteries that are each 1.5 volts and we add them up, minus plus, minus plus, minus plus, the total voltage of this composite battery is actually 6 volts. All right, by the same token, if we were to take 6 of these things, and that's how that 9-volt cell was developed. Let's take a quick look at that. Go back on the Zoom screen, and there's our 9-volt. And if you recall, I showed you that inside of this fits those very small, like quadruple A batteries. There's 6 of them, and each one of those are 1.5 volts each. All right. Okay, so again, if we take each one of these smaller batteries and they were 1.5 volts, we'd get a 9-volt cell. So that's how batteries add up in series. So they add up, you sum them up in series if you connect them minus the plus, minus the plus. All right, now the parallel addition of batteries is a little more tricky. Let me show you that. So if we take 4 batteries and say each one of these batteries was 1.5 volts, all right, and we put them all in parallel, plus to minus, plus to minus, plus to minus, and then we tied all of them together here, and that's the minus, and we tied them all together here, and that would be the plus. We would have a total output of 1.5 volts, so the voltage would stay the same. But now each one of these can source the current. So when we hook up this composite battery up to a device and it requires some current, the final current is going to be distributed between these 4, or sourced between these 4 different batteries. So some of the current will come from here, some of the current will come from here, some of the current will come from here, and some of the current will come from here. Now, the tricky thing about this is, even if these are 4 identical batteries, Every one of these batteries is slightly different. It's going to be, each one is going to be at a slightly different level of discharge, and their internal impedance or internal resistance will be slightly different. So if we look at the real model of what's really going on, it's a voltage source and then plus a resistor, and all of those are in parallel. So keep that in mind. So it won't be perfect. So if you build something like this, one of them might put out 100 milliamps, another one might put out 110, another one might put out 90, another one maybe put out 80, and so forth. They won't be totally balanced, all right? So keep that in mind when you put things in parallel. And now another thing that's really important is that when you do put things in parallel or you put them in series, is that you put their polarities correct, all right? So right now you see all the pluses are in the same direction, all the minuses are in the same direction, and the same thing with the series example, right? Minus the plus, minus the plus, minus the plus. It's not, you know, minus, plus, plus, minus. Each one of them is going to add up. So you can think of this as 0, and this is some positive voltage, and then we add that to this 0, some positive voltage, and we keep adding this up. So that's how you put these. So always minus, plus, minus, plus, minus, plus, and when you put them in parallel, then it's minus, 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 plus, 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 all right? But you don't want to put them in such a way that you cross things. So for example, let's do a series and parallel example where we kind of put the polarities in the wrong direction and kind of take a look at that real quick and see what we're dealing with there. All right, so let's go to the drawing board here, and let's pick a color here. All right, so let's see. Okay, so let's start off with our first one, and let's assume that we have one battery here, and let's take that and let's put this one in parallel with another. So now we're going to put it in parallel with another. Okay, so that looks good, and this is ground here, and this is one of the symbols for ground. It's kind of an arrow going down. Another symbol is almost looks like a battery. That's another symbol for ground. All right, and ground is just a reference, and we'll learn more about this later, but it's just a reference. And okay, just a reference point. It's typically, you know, 0 volts. Okay. All right, so now this is plus, this is minus, this is plus, this is minus. This is a parallel configuration. So up here, let's say that these batteries were, let's just say that these were 9-volt cells. Okay, so these are our prismatic 9-volt batteries like the one that we just looked at. Okay, so far so good. So if we go over here and we take our meter, and we were to take our meter and we put our meter like this, and we measured what the voltage was with our voltmeter here, so voltmeter, and we measured it, we would see that it's 9 volts. So all is good, and everything is good. Okay, now if we were to look inside here a little bit, and what does the real model look like? Well, the real model looks like this. There's a resistor here, and there's a resistor here, in kind of idealized batteries. So this is really what's going on. So now let's kind of draw some dots, and these will kind of represent nodes. All right. Now, if we were to cross these over, all right, what is going to happen? So if we were to flip one of these and put these in the wrong polarity, all right, so they're not exactly going to cancel out. So let's see what the actual circuit looks like. So, and let's do it down here. So we got this guy right here. We've got his resistor, its resistor. All right, and we got that that resistor there, and then we've got this situation here, and like this, and then we've got our ground here, and then this would be our plus node. This would be our plus node here, plus node here. That's what we think it is, right? This is ground. GND is another version, abbreviation for ground. All right, and this is plus, and this is minus, and this is plus, and this is minus. And let's just call this R1, and we'll call this R2. All right, call this R1, we'll call this R2. We don't know what they are, but they're very, very small. So when this battery is just sitting in this configuration, so what's happening here? So actually we've created a series system, right? So what's going to happen is if we call this, say, 0 volts right here, then we've got the 0 volts here, and now we're going to have current from this battery is going to be pushing out through here. All right, and now it's going to go through this resistor, it's going to go through this resistor. Now we have another voltage source here. So this one here would be our first 9 volts, and this would be our next 9 volts. So in this configuration, what we'd actually end up with is something that looks like this. So if we want to kind of start this as a reference point, right, what's going to happen is this. We're going to start off, and we've got one battery tied directly to this battery. So we've got one battery tied directly to this battery. And then we've got these 2 resistors here. All right. And so what's going to happen is we're going to get a current, and this is going to end up looking like the series circuit that we had above. So there's going to be a current that's going to flow here. And the problem with this is we've got a closed loop here. So whatever these internal resistances are, and they're very, very small, let's just say that they're 1 ohm. Okay, let's just say that they're 1 ohm, and that's the symbol omega for resistance, 1 ohm. And again, we don't exactly know how to do circuits, but we're going to kind of cheat for a second and do this one. So let's forget about the ground for a second, and let's take a look at what this circuit looks like. So let's kind of come over here, and when you're doing circuit analysis, we're going to learn to kind of simplify things a lot. All right, so what we have here is we've got one battery like this, so that's this guy, and then we've got this other battery, which is like this. And then this thing right here, we're kind of calling this ground. It's just a node, it's just a reference. This is plus, this is minus, this is plus, this is minus. All right, and then the way we've drawn these 2 resistors, they're both going to be right here. There's one of them. There's the other one of them. And this would be R1 here. This would be R2 here. Both of them are equal to 1 ohm, equal to 1 ohm. And each one of these is equal to 9 volt and 9 volt. So we've turned our parallel circuit accidentally into a series circuit. So now the 9 volts are going to add up. So what are we going to have? So from this point to this point, we're going to have 18 volts. All right. And then in a couple, maybe the next lecture, we're going to learn about what's called Ohm's law. And what it says is voltage equals current times resistance. So we're going to learn about that. Voltage equals current times resistance. And we're going to also learn that resistors add in series. So in this case, we have 18 volts. All right, that's the voltage. And then the current, we're trying to figure out what I is here. And we know what the resistor is. 1 ohm plus 1 ohm is 2 ohms. All right, or I equals 9 amps. In other words, we shorted these batteries together by putting them in opposite polarity for a parallel configuration. So what's going to happen is this is not going to burn out immediately, but it will within seconds to minutes, because we're going to cause this thing to punch a ton of current out, put out a ton of current, 9 amps. If these batteries can support that 9 amps and however long they can do it, they will, and they'll start overheating this configuration. So that's really bad. So this is why batteries can be so dangerous. So when you have, for example, lithium-ion batteries, these things have enormous amounts of current supply, or car batteries, right? A car battery, what do you think a car battery can put out for current? So here, 12-volt car battery, right? And, 12-volt car battery, and they're pretty big, all right? And these are lead-acid batteries, okay? So that's their chemistry. So lead acid, and the question is, how much current do you think? 1 amp, 10 amps, 100 amps? How about 500 to 1,000 amps? That's how much a car battery can put out. So if you were to take a wrench, take a wrench and drop the wrench over the 2 leads, that is the worst wrench I've ever seen. If you were to take, let's do that in another color. If you were to take a wrench and drop it over the 2 leads, boy, we gotta work on that. All right, there we go. So there's our wrench. Okay, a little bit better. Okay, so if we took a wrench and dropped it over the 2 leads, it'll actually melt that and liquefy it. That's how much current is available in a car battery. So, but in the batteries we're talking about, these small primary batteries, D cells, C cells, whatever, they can't really put out that much current, but still it's going to overheat and damage the circuit. So that's what happens when you would put the parallel configuration into a series configuration like this. So this is not going to be good for us, all right? Now, let's take a quick look at the other configuration. So if we have, go to a different color. So now say we were trying to do a series battery. So okay, we take our cells here, and let's go like this. and we put them together. Let's say we did 3 of them. All right, so we had something where we wanted to get about 5 volts. So we took 3 1.5 volt cells. Maybe they were D cells, right? So we take 3 1.5 cells and we put them in series, and we go here and we take our meter, and we're gonna, let's call this side ground here. So we'll call this ground, right? And we'll call this plus. And we take our meter and we hook it up to this, and here's our meter. All right, and this is our voltmeter. And what would it put out? It would put out the sum of these 3 things, which would equal 4.5 volts. Now, what's really going on in here is each one of these has an internal impedance, a resistor inside of it, right? And each one of these batteries, right? And here's really what each one of these batteries looks like, right? Each one of these batteries, and this one. Okay. And, so we could call that R1, we could call that R2, we could call that R3, right? And so we've got these small impedances. Again, these are like on the order of an ohm or so, all right? And we're putting these all in series like this. And of course, the polarity in this case, this was, plus and minus, so they keep adding up, plus and minus. And so here we would call this 0 volts, and then over here, this would be 4.5 volts, right? Okay, so that's all fine and dandy. Now, when we start putting a load on this and start drawing current from it, then what's going to happen is some of the voltage is going to drop over each one of these little internal resistors. So we're going to drop some voltage over each one of these resistors, and so the battery, right, is going to be supplying the current, and each one of these batteries is going to drop some voltage. So overall, the battery is going to have less of a voltage on the output. So as we draw more and more current from this, the 4.5 will decrease. All right, so when it's a little bit of current, like 1, 10, 20 milliamps, it'll hang at 4.5. But as we draw more and more current, it's going to drop 4.4, 4.3, and so forth, and drop down. All right, because remember, nothing is ideal. Everything is, we use idealized models, but at the end of the day, we have to look at what's really in there if we push these things too hard. And that's the whole purpose of digital electronics. We use extremes so that we don't have to worry about a lot of these things. Okay, so now the question is, what happens if we start flipping these things around, right? We start flipping these things around. And again, we don't really have the tools yet to figure this out, but just to do a quickly show you, let's go ahead and just erase all this real quick. All right, so now let's just do this. So here's our first battery and our internal impedance, okay? And this is minus and this is plus. All right, and then now we're going to connect that the wrong way to another battery. So here's the resistor. Here's the resistor, the internal impedance. And so this one's R1 and this one's R2. And then here's the plus sign, the plus side, like this. Okay. All right. And now here's minus and here's plus. And we set each one of these as 1.5 volts. Okay. So now we don't have a short, so this is good. So now when this thing is just sitting here, nothing is going to happen to it. It's just these batteries are just in the opposite direction. So nothing's going to happen to this when it's just sitting here. But if we were to now create a circuit from this and now feed this into something and connect it to something, right, some kind of load, so say another resistor or something, and we'll just call this R, N, some other load, and this is just a load that we're powering, right? This is the device that we're powering. Then it's like you've got one battery, a resistor, and another battery, and another resistor. So what really happens here? So these things are going to fight each other, all right? And then how we really do this calculation, we can do it with a technique called superposition. But each one of these voltages and each one of these resistors, we can just kind of work with and work through here. And we're going to learn how to do this later. But at the end of the day, what's going to happen is this. If this was actually 1.5 volts and this was actually 1.5 volts and this was ideal, right, and these resistors were absolutely equal, then what's going to happen is we're going to have a zero potential here. This would actually be perfectly zero and nothing would happen. There would be no current flow. So these two things would cancel out. The two electromotive forces would cancel each other out. But in reality, no matter what, these things are never going to be balanced. One of these, so you could think of at this point here. So this battery is pushing current this way. This battery is pushing current this way. And so the net current, so we've got one current in one direction, one current, so we call this, I, could call this I plus, we could call this I minus, the two different directions. The final current in the circuit, right, and we could just call that final current, that is a horrible arrow. We could call that I. So I would equal I plus plus I minus. All right. Now, in a perfectly balanced circuit, this would be 0. But in reality, these will never be perfectly balanced. So I will be some small amount. And the other bad part is that current is going to potentially flow in the wrong direction through these batteries, which the batteries don't like. So you don't want to put the batteries with the wrong polarity. You want to put them minus plus, minus plus, minus plus. You don't want to put them like this. It will work, and you could make this experiment and you could see what is going to happen, but it's not going to make the battery happy. So batteries don't like reverse voltages, and they don't like currents going in the other direction through them. All right, so anyway, so that's series and parallel, let's come back here. That's a series and parallel addition of batteries. All right. And then the last two things here that I want to talk about, I think we have a little bit more time here. I'm trying to shorten these up a little bit now because I want to get the pace going, is being able to generate a voltage with magnetic field. So Michael Faraday, and again, I'd like to say the names of people so we kind of heard it once. His law of induction, it states that when a conductor is passed through a magnetic field, a current is generated in the conductor, or if a stationary conductor is placed in a changing magnetic field, the same will occur. All right, and that's called electromagnetic induction. So in this case right here, here's what's going on. So the X's are a magnetic field, which is usually labeled B, and it's going into the paper. That's what the X is. If we wanted it out of the paper, we'd see little dots. That's the kind of convention. All right, so we've got this magnetic field that's going into the paper, a B field, and then we have this conductor right here. All right, if we move the conductor through the magnetic field so it cuts the magnetic field at a velocity v, we will actually generate and induce a current in this conductor. So this is really, really cool. This is the basis of generators, alternators, motors. All of these things are based on electromagnetic induction. So that's really cool. All right. Now, if you take that idea a little bit farther, here's how, for example, a motor works. So you've got permanent magnets. If you take apart a motor, you'll see this. Permanent magnets, you've got a north pole and a south pole. Then you have a coil of wire or coils of wire, many coils of wire. There's lots of ways to build motors. Anyway, you've got this coil of wire, and then you've got these two kind of slip rings that make contact so this thing can actually rotate. And as this wire rotates, it's going to cut through this north and this south, and then a current is going to be generated here. So here's the thing. So if, for example, you have some kind of mechanical system that's turning this, that would allow you to generate current. Or if you flip it around, now here's the interesting part. So if we had a mechanical system, say the shaft, right, was connected up to, say, a water wheel or a windmill. As that mechanical energy rotated that shaft, that would rotate this wire or coils of wire in this magnetic field and generate a current for us, and we would see this current kind of coming out here. Now, by the same token, if we reverse that, if we inject a current into this coil of wire, then this coil of wire is going to have a magnetic field itself, and it's going to push against this north and this south. And then if we construct this motor in the right way, we can get it to continue to rotate. So we can convert electricity into rotation or rotation into electricity. That's what a motor does, and what a motor and an alternator and a generator, and those are all variations of the idea. Okay, last thing I want to talk about real quick here, and we're going to kind of put this to bed, is the photoelectric effect. And so this was Einstein's work, and I believe, and I'm not going to Google it because I hate Googling everything because it just seems like you know everything. I believe that this is what Einstein actually got the Nobel Prize for. It's not equals mc squared. It's actually the photoelectric effect that he won the Nobel Prize for. You can look it up. I think I'm right. Anyway, so what this is all about is if you have high energy photons and they hit atoms, what happens is that photon energy excites the electrons inside of the atom and ejects them out. So as those loose electrons eject out and move on to another atom, you're causing a current, all right? And so that's the photoelectric effect, and that's what photocells, silicon cells are based on. All right, and the one interesting thing about this is it's not based on the intensity of light, how many photons, but on the frequency of light. Because if you remember back to I guess quantum mechanics, the energy of a photon is the frequency of it. That's it. It's just the frequency of it. It's not how many photons. All right. So if you look at this equation right here, the electron volts, energy in electron volts is h times the speed of light over the wavelength, and h is Planck's constant. All right, and c is the speed of light, and lambda is just the frequency. All right, and there's those values right there if you care about that. All right, so that's it for this section, and so now we're going to finish up, and we're going to come back, and we will talk about alternating and direct current next. All right, and so that'll be interesting. So I'll see you then. Bye. All right, welcome back, and we are on the next lecture here. So we're going to continue talking about types of current. We're going to start off here and talk about the differences between alternating current and direct current. All right, so in digital electronics, we're typically talking about direct current. And so direct current means that the direction of the current is always going in one direction, and it's not alternating back and forth. So now, but here's the thing. The word direct really is the wrong word for this. It's not direct or indirect. It is, it's simply staying, the current's always moving in one direction. The word alternating means that the sign of the current is changing back and forth. So it's going positive to negative. And that's really important. So for example, your outlets at your home, your AC electrical outlets, those are alternating current. So for a moment, the current is flowing in one direction, and then the actual polarity completely switches and it's flowing in the other direction. All right. So we're going to talk a little bit more about it, and we'll have some examples. All right. So now let's start off here and talk about direct current. So in a digital circuit, for example, we've got a DC source, and this DC source might be 5 volts or 9 volts or 3.3 volts or whatever it is, and that's powering our circuit and our digital ICs. And so the circuit itself, it's direct current. Now, in a digital circuit, we can certainly have signals that vary up and down, and they change. All right, so for example, we could have a square wave, or we could have some kind of other digital wave that changes as a function of time. But what it won't do is change polarity. So it'll always be in reference to zero. So the current will always go in one direction. The voltage may vary up and down, but it's not going to switch directions and go in the other direction. And I'll show you an example in a second. All right, so let's talk about a quick example here of a simple direct current circuit. So looking here at the little flashlight, so this is a good example. So we've got a battery, a voltage source, and again, we don't exactly know how circuits, we don't have our laws down yet, but we're going to get to them very shortly. But we've talked about voltage, and so we've got a battery here, and one rule of voltage is that whenever we have a conductor, the voltage is the same in the conductor no matter where the position of the conductor is. All right, so let's say that this was say a 1.5 volt battery, or a 6 volt battery, or a 9 volt battery, whatever that voltage is. And if we were to call this 0 right here and put a ground there, whatever the voltage is at this positive terminal, the voltage will be the same here, and the same here, and the same here, and the same here. It'll always be the same. So basically a conductor, whenever you have a conductor, the voltage stays the same. Now, an interesting thing is there's no such thing as a perfect conductor. So the voltage, actually, there is a small voltage drop because the conductor does have a resistance, and each one of the materials has a certain resistance per foot. All right, silver, aluminum, copper, gold, and we kind of talked about that a little bit. All right, anyway, so the whole idea here is we flip this switch, and then this battery is connected to this bulb. Current's going to flow through the bulb, and that's direct current. All right, and notice we're never switching polarities here. We're just the battery's turning on, and the negative is staying in the same place. The positive is staying in the same place. All right, and then we just have some symbols here for different kind of voltage sources, which we've already talked about. We have our battery with our plus and our minus here. All right, voltage source. Then we have kind of a voltage source that we don't really know what it is. So it's something electronic, so it could be a power supply or something else, plus and minus and a voltage. And again, with conventional current, its current is going to flow out of the plus terminal always. And then we have this last one here. And so this is a controlled source. And really quickly, a better symbol for this is the diamond for a controlled source. And all this means is there's some control variable that controls what the actual voltage is. So let's take a quick look at this right here and look at it a little bit. So let's see, what color do we have here? That's good. All right, so we had our battery source and we had our just a voltage source with a little circle, but now we've got a controlled source, and this is called a dependent source. And so we have plus here, we have minus here in this example. And then now let's actually make a circuit here. And again, we still don't know all the laws yet, but we're going to get there. All right, and so we've got a resistor, we'll call this R1. All right, and this is a plus here and a minus here. So here's our source, and let's say that the voltage of the source equals some function of a variable x. All right, so the voltage equals some function of a variable x. So here V is the voltage. Let's say that the function x is 2x plus 2. All right, so in this case, let's make a little table here. And so here's, we'll say is x, and then here we'll say is v. So if we put x equals 0, so then we have 2 times 0 plus 2. So at x equals 0, we've got 2 volts. Let's make x equal 1, so then we've got 2 times 1 is 2 plus 2 is 4. All right. Now let's let x equal 2, so we've got 2 times 2 is 4 plus 2 is 6, and so on. So what this is a line, right? If you recognize this, this is just simply a line. So in this case, we've got the control variable is x, and the function is 2x plus 2, and the voltage follows a kind of a linear curve here, right? And so the whole idea here is whatever controls x drives this circuit, and x could be, you know, some sensing component, could be another part of a circuit, but the point is that somehow we create this controlled source, and then this input variable x controls it. All right, so now, so let's see, what would we call this? So this is a, and let's also say that x is a voltage. All right, so let's say that x is some kind of voltage. So this is a voltage controlled voltage source, because this thing is going to put out a different voltage, right? V equals f of x, which is this right here, depending on a voltage, and we're saying that x is a voltage. So this is a voltage controlled voltage source, voltage controlled voltage source. Now let's say x could also be a current, right? So x could be a current. So the voltage could be f of x, and x could represent some current in the circuit. We don't know. So that would be a current controlled voltage source. All right, and then you can see we can have all kinds of permutations of these. Instead of a voltage source, we could have a current source, right? So we could have a voltage controlled current source, and so on and so forth. So you can have all those different versions. So this is kind of the basis of you know, amplifiers and one circuit controlling another circuit, and ultimately these things are voltage controlled voltage sources, or current controlled voltage sources, or you know, current controlled current sources, all kinds of different versions of them, right? Okay. So let's move on and go back here. All right. Okay, now I want to bring your attention to this figure right here. So we're going to kind of talk about this for a second. All right, so now let's talk about let's go ahead and let's talk about alternating current. All right. So to talk about alternating current, the best example of this would be your current coming out of your wall socket. All right. That's an alternating current. And in the United States, for example, this is 120 volts. And it's 120 volts root mean square, which we'll get to what that means in a second. It's a kind of a measure of average. It's 120 volts root mean square, and it has a frequency of 60 hertz. All right, so it's flipping back and forth 60 times a second. All right, now in this example, and this is, oops, this is a little typo right here. So this should be +5 and this should be -5. All right. Oh, actually, no, it's correct. This is +5 and this is -3 volts. And it could be anything. And this is just showing an example. All right, so let's take a look at this and kind of look at some of what these labels are. All right, so here we have a sinusoid. So this is a pure sinusoid. So this is a sine function, a sine x function. All right, and so some of the things that we can talk about is if we look at 0 volts, all right, that's kind of the reference. So from 0 to the positive peak, that's one peak. All right, so that's the positive peak. And then 0 to the negative largest peak, that would be another peak, and that would be the minus peak. All right. So we call the peak going from 0 to the highest voltage, we call that P max. So that might be VP max, V peak max, V peak max. And then the lowest voltage, we might call that V peak min or VP min. All right. Now the total travel or as the voltage goes up and down, it's going all the way, in this case, from 5 volts all the way down to -3 volts. So there's a total of 8 volts of travel here, right? So if we were to subtract these two things, the top peak minus the bottom peak, we would get 5 minus -3, or there'd be an 8-volt transition. So there's a total of actually 8 volts here. All right, now some other things. So here's one cycle. So this is a periodic function. Sines are periodic functions. Sines and cosines are periodic functions. And they repeat themselves. So we only really need to be able to analyze one cycle of this. So the length of the cycle here, the period, we're going to call that t. All right, and in this case, this axis here, the x-axis, has actually been labeled as time, t, in milliseconds. And we're saying that the time it takes for one cycle, you can see this is 1 millisecond right here and 2 milliseconds right here. So if the time it takes for one cycle is 1 milliseconds, then this little equation here, the frequency is 1 over t, or 1 over the period. So again, I had mentioned having calculators really, and instead of using the computer, and you really want to do this, it's much better. So there's a really good calculator, a TI, but we'll go ahead and use this kind of simpler calculator. And so if we take 1 millisecond, we say 1 over 1 millisecond, so 1 divided by 1x to the -3, right? And then we're going to get 1,000, of course, right? 1,000. And that's 1,000 hertz. So that means that this particular sine wave has a frequency of 1,000 hertz. It's got a maximum peak of 5 volts and a minimum peak of 3 volts. It's got a peak to peak of 8 volts. Okay, so those are some of the things that we can talk about when we're talking about a sine wave. And now your AC circuit coming from your wall is a sine wave. Now in the United States it's 60 hertz. In many European countries it's 50 hertz and so forth. And the connector is a little bit different. But now let's talk about some of the different ways that we measure what the voltage is here. So since it's a sine wave, it's going up and it's going down. So when you look at that 120 volts on your socket, is 120 the peak voltage? Is it the highest peak? Is it the lowest peak? Is it some kind of average? And the problem is with these things is finding an average is difficult, because if you look at this, it's positive up here and then it's negative the exact same. It's a reflection. So if you were to average this thing out, this would actually cancel out to 0. So we need some other way to compute an average, all right? And the other way that we're going to do this is called the root mean square. So let's take a look at what root mean square looks like. All right, so let's move on here a little bit, and okay, and put this up. So what I want to do here is I want to show you something, and we're going to kind of derive this a little bit. Okay. Okay, all right, so let's take a look at these equations here. So this first thing says XRMS equals the square root of 1 over n times the quantity of x1 squared plus x2 squared plus 2xn squared. So to compute the root mean square, which this is a kind of a method of finding an average of a signal. And so we want something that has some meaning. And so this RMS value, root mean square, is just a mathematical way to kind of compute an average so that it has some meaning for periodic waveforms or sinusoidal waveforms and so on. Now there's a discrete version of it, which is this right here. So if you have a number of discrete values, x1 through xn, and you want to compute its root mean square, then this would be the formula. So let's see, where does the root mean square come from? Okay, so the root is the square root, and that's out here, right? So there's a square root, okay? So that's that piece of it. Then we have the mean, all right? So that's that 1 divided by n. So if you want to find the average of something, you divide by how many elements, all right? And the square part is we take each one of these samples and we square it. And the reason why we square it is to get rid of the negative value. So we just want the magnitude, positive or negative, we just want the magnitude no matter what. So if you take a negative number and square it, you're always going to get a positive number. So we basically are finding the average of the squared values. Here's the average, and then we take the square root of that because we squared everything. Right? So we need to undo that, and then we find the square root of it. So that's the root mean square. So if you had a discrete signal of values, say it was an audio signal, which is a bunch of samples, this would be what you do to compute it. Now, let's talk about something a little bit more complicated, which is our sine wave example. Damn it. Okay, so this version of the formula right here, this is a calculus-based version. So if you know calculus, you'll kind of understand this. But if you don't, it's fairly common sense what's going on here. So let me kind of translate this a little bit. So in calculus, the symbol here means to integrate. And integration is a method of summing something up. So to sum up, if you want to sum up a function, what the integral does is it takes it and it breaks it into teeny tiny little pieces, and then it sums each little piece up so that they get infinitely small, and there's an infinite number of them, and you sum them all up, and so that's what an integral does, all right? So this is basically just a summation, so it's equivalent to this. So this integral is equivalent in the discrete domain. The integral in the continuous domain is basically a sum, all right? Cool. Now, what do we want to sum? We want to sum some function, and this is going to be our sine function, but we need to square it. Okay, so this sine function here would be our sine wave, which represents our AC signal, and we square it. And then we want to do this integration and do this process over the time period that this is occurring. So this is what this T1 and T2 is. So from time T1 to time T2, we're going to integrate and sum this all up. Then we need to find the average, so we need to divide 1 over T2 minus T1. All right, now since we're only going to do one cycle, that's all we need to do the root mean square. Since we're going to just do one cycle, the final equation will look like this. Forget this limit right here. So it'll just be from 0 to whatever the period is, right? Whatever that time is for one period. And then it'll be our function, f of t, which in this case is going to be a sine function squared. And then we just divide by 1 over t and then take the square root of that. When we're all done with that, and you do the math, the interesting thing is that everything falls out of it. Everything falls out of the equation, so the time falls out of it, the sine falls out of it, and all you're left with is this down here. So for a pure sine wave, the peak-to-peak value equals 2 times the square root of 2 times the root mean square. So 2 times the square root of 2 times the root mean square. So we can use this right here, and we can, move this around in different ways. All right, so let's take this and let's move it back over here. And let's look at what's over here. So if we look at what's written down here, it's kind of the same thing. So the root mean square is 0.5 times the peak to peak divided by the square root of 2. And this 0.5 is the same as 1 over 2, right? So let's let's write these down and so that we have different versions of this and kind of see what we got. So let's go over here and let's take this and erase this. And this is important because you can just move from one to the other. Okay, so we're saying that the voltage peak to peak equals 2 times the square root of 2 times the root mean square value. All right, which that also means that, and we're just going to take this 2 square root of 2 and move it over to the left here. So V peak to peak over 2 times 2 square root of 2 here, 2 times the square root of 2, equals the RMS value. All right, so, and just flipping sides around so that we're not backwards here. If we take the V peak to peak times 1 over 2 times the square root of 2, that is what the RMS value is for a pure sine wave. So this equation right here is all we need. All right, now if you compute what this 2 times the square root of 2 is, right, and just leave it as a number. So let's take a look and let's see what that is. So let's do it. So we'll take the square root of 2, which is 1.4, and this number is going to come up a lot. So the square root of 2 is 1.414, and with some decimal. All right, so that's an important number to kind of have a feel for. Whenever you do the square root of 2, that's that. All right, so 1.414 times 2 equals 2.8. So let's so the 2 times the square root of 2, of course, is going to be 2.828 with some decimal. We'll just leave it like that. All right, and that's this part of it here, right? Okay, and then when we take the inverse of that, we're going to get 0.3535, all right? So we're going to get 0.3535. So the root mean square equals V peak to peak times 0.3535, all right? And so this can be used in a lot of different ways. You can leave it like this if you want to on your calculator, but what's cool about this is this allows you to kind of figure out different things. So you can figure out the peak, you can figure out the peak to peak, you can figure out the root mean square, all from this equation. So we said that a typical wall socket in the United States, so a wall socket, right, an AC outlet, is 120 volts at 60 hertz. So the 60 hertz doesn't really matter here. It's 120 volts. So if we look at the sine wave, so if we take our meter and we were to, if we could somehow measure this, which we can. So if we were to do that, then here's one peak and here would be the other peak, right? So this would be V peak, max, and here would be V peak min, and of course this is time here, right? And the vertical axis is voltage. So the root mean square is not this peak, it's not this peak, it's this kind of average number. So for 120, what is it? So if we take the 120, so if we take 120 and we multiply times 0.3535, it's let's see, what did we do? What did we do wrong there? We did something wrong there. VP peak. Oh, we don't, my mistake. So what we want to do right now is we're going to compute what the V peak to peak is. Okay, so the root mean square is the 120. Okay, so we're going to take 120 volts and we're going to divide that by this 0.35. All right, and that's going to give us our V peak to peak. All right, so 120 divided by 0.3535. All right, that's better. 339 volts. 339 volts. Okay, and so what that means is that the peak to peak of your AC coming out of a wall socket is actually 339 volts. Now, if it's completely symmetrical, then the positive peak will equal the negative peak. So if we just divide this by 2, the 339 by 2, then we get 169. All right, so that's saying that each one of these peaks, so this is 169 volts, and this would be minus 169 volts. All right, so this is really interesting. A 120 volt wall socket is not 120 volts exactly. The root mean square is 120 volts, right? The actual positive peak is 169. The negative peak is minus 169 roughly, right? And the total transition is 339 volts. So the peak to peak is almost 340 volts. So that's a lot. So if we were to take a meter and measure this, we should get something like this. Okay, so let's go and give that a try. Let's actually take a meter. Let's go to a wall socket right now, and let's see if we can measure this and see if we can get these values. Okay. Okay. So, so what I have here is a wall adapter, and a lot of you use these, I'm sure, to power your computers and whatnot. This one is called a kilowatt, and why it's cool is it has a little LCD display, and it can show you power, voltage, wattage, kilowatt hours, power factor, amperage, all kinds of really cool features that it has so that you can measure things. And it has an off switch and an on switch. And so what we're going to do is we're going to use this, and we're going to actually measure this, and we're going to kind of look and see what we get out of my 120 root mean square wall socket. So the first thing that we'll notice is you see this says 116 volts here, and that's actually the root mean square. Let's zoom in a little bit. 116, so it's not 120. At least this isn't reading that it's 120. And that's another thing. It's, you really need really good equipment to be very accurate. So I've got some other equipment, AC equipment, that's extremely accurate and much more accurate than this. It's probably $1 of electronics in here making these measurements. And even the meter that I'm going to show you in a minute, which costs a couple $100, is still not as accurate as the AC equipment that I have, but it's close enough. Okay. So the first thing is we're going to measure this. So we're actually going to stick some probes into these sockets. And this is very dangerous. And so we're going to be messing around with AC here. 120 volts won't kill most people if you get shocked by it. All right. But what it can do is it can cause cardiac arrest. It could cause, if you were to, say if something were energized, like say if this had, 120 volts and you had grabbed it, you may not be able to let go of it, all right, because our muscles are electrical in nature, they clinch up when a voltage hits them. So you want to be very careful. So the first thing that I'm going to want you to do is put on gloves, rubber gloves, and these are rubber electrical gloves to protect from any kind of shock. All right, and so now, of course, these aren't, if you're going to go work on power lines, these wouldn't work. All right, but for AC, house AC, these will work fine. All right, so I always wear gloves whenever I mess around with AC, and just as a precaution, and I don't care if it's not cool. And the other thing I want you to wear is eye protection. And the reason why is when you're talking about 120 volts, at 10, 15 amps, there's 1,000 plus watts there, 1,200, 1,500 watts of power. That can liquefy metal very quickly. It can cause something to explode, a battery, a capacitor, any kind of electronic component. And what can happen is something can explode and fly into your eye. So you're going to want to wear eye protection. These are polycarbonate glasses. They're very comfortable. They're kind of almost like Oakley glasses, if you know what those are. And so these are really good. These are machinist glasses, so nothing will hit your eye. And you can get ones that completely cover, your face and all that. But we're going to at least do something like this. So this is what I recommend that you get if you're going to mess around with AC, and also for soldering. So I've already got some protective glasses on right now. Okay, now what we're going to do is we are going to take this power strip, and we're going to measure what the voltage is coming out of it, and we're going to kind of look at the peak and peak to peak and all that. So I've got a meter here, all right, and this particular meter, let's zoom in a second here so you can kind of see it. So this particular meter has a couple functions here. So it can measure DC voltage, AC voltage, but what's cool about it, it can also show you DC and AC simultaneously. So what this means is that, say if you were measuring some signal and it had a DC component, meaning maybe it's got a 10 volt DC that's always there, then from that DC component, something modulates up and down, say plus or minus 5 volts. That would be AC. That would be an AC component of it, an alternating current from that DC point. So we can figure that out and resolve it. So our wall socket better be 0 volts, no DC, and it better just modulate around the 0, and we should only see AC. The other thing here is, if you look at the decimal place, I can move the decimal place around with the range button on this particular meter. And I'm going to put it with three digits because we know that we're going to be measuring something 100-ish, all right? Okay, so we got that. All right, we've got our probes in voltage in common, all right? And so let's zoom out of this here a bit so you can kind of see that. And then what I'm going to do, I'm going to just try and fit this all on here so you can kind of see everything, all right? And one other little detail is let's put this over here a bit. The power strip itself has a safety feature or a kind of a power saving feature. And you can turn this on, you can turn this off. If you turn it on and there's no load, it'll actually turn itself off in a few seconds, and it just did. You can see that no load blinking on the LCD. So it actually turns the power off as a safety feature, so which is really cool, but really annoying if I want to test these one of these sockets, right? So what we're going to have to do is we need a load. So what we're going to use as a load is a simple AC wall adapter here. So this is a little 12 volts, 9 volt, little 9 volt, 300 milliamp DC. So this has got a transformer in it, which we're going to learn about, and we're going to use that as a load. So now watch what happens when we plug this in. We'll plug it in down here, and then here's what the end of it looks like. It's a little barrel connector, which is real common. All right, so now this thing's working. You can see the green light turned on. So first thing is, let's actually measure this. So let's measure it. So remember, this is going to be putting out DC. So we better see a DC of 9 volts. So on the DC part of the display, we should see 9 volts. Now, this is a low voltage and low current, so we can't cause too much anarchy by messing with it here. So, but again, you don't want to short anything. So I'm going to put the negative probe inside. All right, so this is tip positive and the barrel is negative, so I'm gonna put that in there. All right, and then I'm gonna put the other probe on the outside. Let me kind of scoot this over. All right, okay, there we go. Okay, and you can look at this here, and it's saying it's 14.66 volts, and you can look at the DC is 14.66, and then the AC is 2 volts. So this is really interesting. So DC, it's 14, and then AC, it's 2 volts. So what this is saying is there's a component of AC on this signal, right? So it's not perfectly DC, and that's exactly true. These wall adapters are just transformers in them typically, and then they have a rectifier and a capacitor, and they're very poor DC sources, so you need regulation. So you really don't want to use these things to power anything unless you have a regulator, a voltage regulator, which we'll talk about later. All right, now another thing that you notice, this thing's supposed to say be 9 volts, right? And it's like putting out 14 volts, 14.6 volts DC. So what's going on here? Well, this is unloaded. So if you were to put a load of 300 milliamperes, then you would get about 9 volts out of it. So what that means is if you have a very light load, say 10 milliamperes, you might get 14 volts out of this. And if you are expecting to get 9 volts, you will blow your component out. So again, be careful using wall adapters and make sure that the thing can tolerate a voltage that's much greater. These are not what they say they are. These numbers on here are inaccurate, and you need to measure them because this is usually a loaded, when it's loaded at 300 milliamps, that's what the voltage will be. But unloaded, it could be much higher, all right? So be very careful of that. All right, so we have a load, and it's loading this power strip. Okay, so now what we're going to do is we're just going to literally, so let's push this over here. All right, I'm trying to get a good view for you guys. Okay, and I'm going to just put these inside, and then each one of these sockets has a neutral, a hot, and then a ground. Neutral and ground are connected, and then the other is hot, all right? And then depending on where you are and what country you are, you'll have something similar. But anyway, so we can measure between hot and neutral, or we can measure between hot and ground. So let's see what happens, all right? So We're going to plug this into neutral and put the other one into the hot lead. Now, what we don't want to do is touch these two things together. Oops. We don't want to touch these two as we're plugging them in here. We will short out, and this has short protection, so it won't blow the fuse in the house, but it is not a good thing. And that's another reason why we have these gloves, because say there was a piece of metal exposed and maybe there was something we didn't notice, we could shock ourselves. That's why we have gloves on. So we're just overprotective because we don't want to get hurt. Okay, so here we go. So keep your eye on the meter, and we're going to plug these in. All right, and it shows 118 volts. All right, and then now look at the display for the AC and DC component. So that's pretty impressive. So it's 118, and the DC component is dead zero. I am pretty impressed. So that is really good. So that's impressive. And then if we look over at this display here, it's saying 116 volts, and this is saying 118. Which one do we believe? Well, we believe the $200 meter rather than the $1 of electronics in the low-cost, consumer power strip here. All right. Okay. So that's that. Now, so we've computed what this root mean square value is here. All right. And so now, can we put this on any other mode here? So if we were to switch this to a pure AC mode, right? So it's got no DC, and again, we'll see 118 here. All right. Now this particular meter won't I don't think it has any other I don't think it has a peak-to-peak mode, but we can go and adjust this, and we can see if we can see some other things. So if we press the adjustment button, which I'm going to do, all right, and that's nothing important. All right, so this, and it's not, I was trying to get it to measure a frequency, but this particular, let's see if we can put it back to here. Let's see if we can get it to measure frequency. And no such luck right here. So anyway, but this is at 60 hertz, and this particular meter does not have this functionality. But anyway, that's why you have many meters that do many different things. All right, so that's measuring something with line voltage. And so the root mean square of this is about 118, but we'll call it 120. And if we take that to 120 and we were to compute the peak-to-peak value like we did over on the board back there, over on the presentation, we saw that we had these plus and minus voltages of like 100 and what was it? It should be 169. Yeah, 169 volts. All right, so now the question is, what would happen if we put the meter on a DC mode and then we put an AC voltage into it? All right, so the meter's on a DC mode and we put an AC voltage into it. So the first thing is we need to make sure that the meter can handle it. All right, so we're going to take the meter here, and it's on DC mode, and the problem is I don't know in this particular meter if it'll let us do this, but let's see. All right, and then we're going to measure this. Yeah. So in this particular meter right now, you can't see it, but it's measuring almost nothing for DC, which is what it should do. What I wanted to do is I wanted to see if we could measure the extents. So in AC mode, if we could measure what the extents were, the peak extents, but this meter unfortunately does not have this functionality. So anyway, so that's it. So that's measuring something, and so let's turn this off. That's measuring something, measuring line voltage, and that's what the root mean square is, and that's what AC is. So that's what alternating current is. It's going back, it's going forth, and it's alternating beyond the zero threshold. All right, and direct current always is going in one direction, and it doesn't go below zero. Okay, so we're back over here, and let's see here if we have anything else interesting before we move on. I think that's about it. So this next subject is important, and I want to spend some time and make this its own lecture. So Ohm's law and power, which we're going to talk about, and we're going to do some hands-on. We're going to build some circuits with this one and with some LEDs, and this will be a lot of fun. So go ahead and finish up here, and I'll see you in the next lecture. Bye. right, welcome to the next lecture. And so now we are going to talk about, finally, Ohm's law and a little bit about power. So we're going to do more hands-on in this lecture. So we're going to kind of move through some of this material at a little bit of a quicker pace. And then we're going to do a lot of hands-on stuff. So this is going to be a lot of fun, and we'll see what happens here. And one thing to remember is, there's just a lot of material. We just have to go over a lot of different things that we have to understand. A lot of different formulas, a lot of different, pieces of technology, and it's just going to take some time. So anyway, bear with me here as we get through this material. So, we'll get to the point where we have enough fundamentals where we can start building things and working with Circuit Maker and kind of laying out circuits, but we really do need to know what we're talking about, and there's just no way to get around this. So we got to go through this stuff. All right, so Ohm's law. Okay, so this is the crux of everything, and Ohm's law, which was derived here, created by George Simon Ohm in the 1800s, all right? And the law is very, very simple. It says that the voltage equals the current times the resistance. So voltage equals current times the resistance of any circuit element, or V equals I times R. All right, and now one little thing, depending where you read, instead of V, a lot of times you might see E representing voltage, E instead of V, but we'll be using V for voltage. All right, so V equals I times R. You must memorize this. If you memorize nothing in electronics, memorize V equals I times R. And then, of course, we can make variants of V equals I times R by dividing things. So current equals voltage divided by resistance. Resistance equals voltage divided by current, and so on, right? So that's Ohm's law. And we're going to go through, a lot of examples that use this basic law to make computations when we get into circuit analysis. All right, so keep that in mind right now. And we're just going to look at we'll look at this example here, but we're going to actually do some on the board, on the computerized blackboard, some more examples. But here's a simple one. So say if we have 5 volts. So we've got a 5-volt source, voltage source, plus to minus. That's going to generate a current, and conventional current's going to flow out of the plus, and it's going to flow through the circuit. And so one thing here is, now let's talk a little bit more about circuits. You have to have a complete loop, for one thing, for a current to flow. So this is a complete loop right here. So current's going to flow. It's going to flow through this resistor, and as it flows, a voltage is going to drop plus to minus. So there's 5 volts here. The entire voltage will have to drop plus to minus over this one element, because this node right here, and let's highlight this bottom node is kind of the reference. So this is 0 volts here. Then we move up through the battery. This will be plus 5 volts right here. All right. And so we've got this 5 volt potential. And now we've got a current. The current's going to flow, and then the voltage is going to drop. So voltage drops over resistors, and the entire voltage will drop. And then we're going to have this current. So if we use the equation V equals I times R, therefore I equals V divided by R. So 5 volts divided by 1 kilo ohm, right, equals 5 milliamps. That's it. That's all there is to it. Let's do this one. Let's say that our voltage equals 50 volts this time instead of 5 volts. And now let's say we have a 500 ohm resistor. Again, so we've got 50 volts. The voltage is we're gonna say that this is 0 right here. We got 50 volts at this node. We'll have 50 volts here. Remember, voltage always stays the same in a conductor. Now we're gonna have a voltage drop over the resistor. Again, we want to compute this. So voltage equals I times R. In this case, if we were told that the current was 100 milliamperes, then we would say 100 milliamperes times the resistance. So 100 milliamperes times 500 ohms equals 50 volts, right? And let's just make sure. So again, get your calculators out. 100 and milli is to the minus 3, right? So X minus 3 times our resistor, 500, and sure enough, we get 50 volts. All right, so and get used to that. Get used to using K and milli. So K is 1,000, milli is 1,000th. those are going to be very common, or micro, which is 10 to the minus sixth. And so you want to get a good feel for those. All right, so here's a couple really simple circuits doing that. All right, so let's get rid of this. All right, and let's keep moving through here so we can get to the good stuff. And we're just going to skip over this, see if anything else is interesting here. All right, so understanding power. All right, so this is important, and we need to know how to compute this. So the definition of power is right here. So the change in power equals the voltage times the change in charge per unit time. So voltage times the change in charge per unit time. So in other words, it's the amount of charge that passes through the element, right? The amount of charge that passes through an element as a function of time times the voltage that element that's across that element. All right, that is going to be power, and power has to do with work, right? So power is actual work that we're expending. Now, if you remember, dq dt, it says it right here, even dq dt is actually I. So the change in work, or the amount of work, equals the voltage times dq dt, divided by dt. And a lot of times you'll just say dq dt, all right, something over something, equals voltage times current equals power, P for power. So really simply, the voltage times the current equals the power. But this isn't exactly true unless the voltage and the current are DC. So if they're DC and they're not out of phase with each other, then the voltage times the current equals the power. Or the instantaneous voltage times the instantaneous current equals the instantaneous power. We're going to get to this in 1 second and why this is a big deal. All right, so let's take a look at some examples here. So if we look at this little figure right here. All right, so in one case here, we've got 1 amp of current, and we have some kind of circuit element, and there's a voltage drop. So it dropped from plus to minus. All right, so this must be absorbing power. So this might be a resistor or heating element or something. All right, so it's absorbing power. So in this case, the sign of the power is positive. So it's 1 amp times 5 volts. So it's going to be 5 watts. All right, let's take a look at this one. So in this one, we flipped the direction of the current, but then also we flipped the direction of the voltage. So again, so the current is flowing upward here, and it's flowing through this element, and the voltage is dropping plus to minus. Again, this would be absorbing. So this is something that's absorbing. All right. Again, it's a positive power. Now here's where things start getting tricky, and this is always confusing. So now something's delivering power. So now we have a voltage source, and the current's going in the direction from minus to plus. So it's coming out of the plus side. So again, if we look up here at our circuit, this is a voltage source, right? This is a voltage source. These are delivering power to the resistor. So this current I is going outward here, and the current I happens to be 5 milliamps, right? So it's delivering 5 milliamps of power, of current, right? Delivering 5 milliamps of current to this resistor, right, which is 1K. And the resistor is dropping this whole 5 volts as well. So again, if we say how much power is being delivered here, so we have 5 volts, 5 times, and then we have our 5 milliamps, 5x minus 3. So in this case, we are delivering 25 milliwatts, all right? And so 25 milliwatts is being delivered, and then 25 milliwatts is being absorbed, all right? So if we come back to this figure here, in this case, we have this situation, which is the same situation as the source in the other figure. We've got a 5-volt supply, we've got current coming out of it, so this is delivering power. And then again, if we flip the direction of the current and we flip the direction of the supply, it's basically an inverted mirror image here. Again, we're delivering power, all right? Good. Okay. Let's see here. Now, let's talk about AC. So computing power in AC is a little bit more difficult, and we have to start talking about, there's lots of, okay, so we're not going to get into AC power, and we're not going to get into AC analysis, and in AC there's instantaneous power, there's apparent power, there's reactive power, there's a lot of different things that kind of come into play. because the voltage and the current are these sine waves, and because they're sine waves, they can have relationships to each other and be in and out of phase with each other. All right. So you can read through this text here in the notes, but in a nutshell, if we want to compute something called instantaneous power in a steady state AC circuit, and steady state means it's stabilized, it's not changing, other than the waveforms going up and down, but the frequency is not shifting and the amplitude, the overall amplitude of these waves are not changing. They're staying the same. Their max and their min is staying the same. So the instantaneous power is whatever the voltage P max is times I P max is going to be the power P max. All right. Now, so let's talk about a couple little things here. So let's skip past this, and I want you to look at this figure first. So in this figure here, what we have are two examples, and we've got a voltage sine wave and we've got a current sine wave. Now, when we're talking about AC, and or we're talking about DC circuits that are riding above ground but still have sinusoids, right? Which could be audio, it could be lots of different signals. The voltage and the current can actually be out of phase with each other, and that can occur when you have reactive components like capacitors and inductors. The current and the voltage is actually out of phase in these devices, and we'll get to that a little bit later. So in this case right here, voltage and current are exactly in phase, and we don't know what this circuit is, but this could be, for example, one case that this will happen is a purely resistive circuit. If you have a purely resistive circuit and you put an AC signal to it, like an AC signal coming out of a wall socket, and we put a resistor, so we take the AC signal, put a resistor, the voltage and the current will actually be in phase. And by phase, we mean that the signals, they're peaking at the exact same time, they're the same frequency. They don't have to be the same amplitude, but their waveforms and frequency are identical. All right. So when this voltage peaks, the current peaks. When the voltage dips to its minimum, the current dips to its minimum, and so forth. In this case, we can just multiply the maximum here times this maximum here. That would tell us the maximum instantaneous power, right? Or we could multiply the negative times the negative, we'd end up with a positive, and that would be the maximum negative going peak power, all right? So again, remember, it's power is voltage times the current. So we could take this voltage times this current, that would give us power of this peak, and then we could take the minus voltage times the minus current, and that would give us the power at this peak. And notice that the power is positive because it's a negative times a negative. Okay, now, see down here it says voltage and current are in phase. So the angle of the voltage minus the angle of the current is equal to 0. So the difference between these two waveforms has a phase of 0. This is really, really important, and that's why we can do this simple calculation. But now, when we come down to this figure right here, this changes a little bit. And let's take a look at this. So if we come here, and let's actually zoom into this one a little bit, and we look at this, we have a different situation going on here. So in this case, we have our voltage, all right, and this is angle 0 right here. So this is like time equals 0, and we have an angle of 0. So we have the sine wave, right, that's going up and going down to VP max and VP min. But we have this current that's out of phase. So you see the voltage peaked first in time. So remember, time is going this way, right? Time is going this way. So this happened earlier in time than this. And if you kind of look at this figure, you can figure out that there's a 90 degrees phase difference in this. All right, so there's a 90-degree angle. So the voltage is leading the current by 90 degrees. And why is that happening? Because in time, moving to the right, the voltage hit its peak first, and then followed by the current hitting its peak. So the bottom line is that there's a phase angle or a phase difference. So if we try to start computing power here, we are going to get zeros. So if we try to use these peak values, so see this peak value times this peak value, so that's a positive number times 0, we're going to get 0. Again, here we're going to get 0. Again, here we're going to get 0. Again, here we're going to get this value times 0. So that doesn't work anymore. And this is why when you're dealing with AC, we have different versions of power, apparent power, reactive power, instantaneous power, and so on, because uh, we have to kind of, figure out based on these sine waves, some value that's useful to us when we're computing power. So uh, if we want to, and because these are sine waves, we can actually write a formula here that will give us this power value if we know that we have sine waves based on this angle. So in this case, if voltage is leading current by 90 degrees or vice versa, you're going to have no power. So there will be no power in this case at these peak values. All right, and so this phase angle, all right, is is something called the power factor. All right, and so let's take a quick look at that. And there's another little equation that governs this. And again, this is more when you're doing AC analysis, and we don't really care too much about this. But so this is right here. So if you want the maximum instantaneous power in an AC circuit, what you really need is to take in consideration this angle between the voltage and the current. All right, so this power factor, this theta right here, this cosine of theta, this Greek symbol theta here, this is the difference between these two angles. That's what this theta is, and this is called the power factor. This cosine term will vary between 0 and 1, all right, and actually between -1 and 1. So now when we multiply the voltage peak times the current peak times this power factor in the AC circuit for the either it's at steady state or when a compute at one specific time the power, then we can use this formula, and this will give us the power when we have a lead and a lag of the voltage and the current. All right, so that's what this is right here. And if you take this a little bit farther and we start computing what the root mean square is of the voltage and the root mean square of the current, so those are those values that are kind of our types of averages. Then if we take the power factor into consideration, and we can use this equation right here, all right? And then we can say, well, how do we compute VRMS? Remember, that's the voltage maximum peak, and that's times 0.707. Remember the whole square root of 2 and 2 thing. And the IRMS is the I max as well, times 0.707. Everything, all the RMSs are the same. You compute them the same way. All right. So now we can figure out this power RMS equals the voltage RMS times the current RMS times this cosine theta term, which is this power factor. Now, the one thing to remember is this cosine theta is not changing. In other words, the lead and the lag is always the same. So if you look back at this figure here, whatever the lead and the lag are, they're constant. So when we have two stable signals for current and voltage, so whatever the circuit is, this phase difference is staying the same. If it modulates, if the phase difference modulates, then we can't do this calculation. We have to do it in a different way where we take into consideration it's changing. But if the lead and lag between the current and the voltage is stable and that angle is theta, then we can say take the cosine of theta, all right, and then we can do this calculation, all right. So what we really want is we want the cosine term to be 1 so that we get maximum power. So now here's a little interesting side note. Your electric company here in the United States, it's one of the biggest ones, is called PG&E. The electric company wants the power factor to be 1. And the reason why is they don't want to, as they send power and distribute power, they want the power being sent to be utilized. So what they don't want is to be sending current back and forth through the power lines and the voltage is out of phase, because then no work is done, and this is a waste. And the problem is that the biggest loads in a home typically are the heating system, air conditioning, big motors, and motors are big inductors, and inductors are going to push the power factor in one direction. All right. So inductive loads like motors push the power factor in one direction. So to push the power factor back in the other direction, capacitors are used. So you take the capacitor and then you put that into a circuit with the inductor, and then you can adjust the power factor so you can get that power factor closer to 1 again. That's why a lot of times when you see power distribution, you see these big giant devices on the power lines that look like canisters. Those are giant capacitors, and what those are for is to adjust the power factor. And when you have a company that's using kilowatts or megawatts, right, that power factor is a big deal. And if that power factor is not 1, you'll be wasting energy and heating things up for no good reason. So PG&E or your power company will get mad at you if you have a really bad power factor. So if you're a big company, you're pulling enormous amounts of power and you're not adjusting that power factor correctly, they'll get mad at you. They don't like that and they'll charge you for it. So, but at residential, they usually don't do that. So anyway, but that's what power factor is. It's the angle between the current and the voltage in an AC type circuit. And ideally we want those to be lined up so that the power factor is 1 and the angle between them is 0 degrees. All right, so but this is kind of power electronics and AC, and if you're an electrician, this would matter, and we'd go into this much more in depth. All right, so, okay, so actually what we're going to do right now is we're not going to do this section now. We're going to come back in the next lecture, and we're going to kind of go back to some of the earlier material with the Ohm's law, and we're going to do some experiments with Ohm's law and kind of work with that with some hands-on stuff. That's going to be a lot of fun. But I just wanted to go through the Ohm's law really quick, kind of teach you V equals I times R, that's it, and talk about power a little bit so we can do that in the experiments, and then a little bit about AC and power factors and whatnot, which you can read more about if you like in the notes. So that's it. So meet me in the next lecture, and we're going to do some hands-on stuff, and this is going to be a lot of fun. All right, bye. All right, welcome to the next lecture, and we're going to continue moving through the material. So we're finally to the discrete components section here of the notes, and we're going to talk about resistors, capacitors, inductors, transformers, diodes, transistors, and maybe a couple other things. However, we've already seen some of these things, and we've already talked about them a little bit. And what I wanted to do before we kind of dug into more theory is I promised to do some hands-on stuff. So we're going to hook some circuits up, and we're going to draw some circuits and do a little bit of circuit analysis and kind of go over Ohm's law again, and with some examples, and then kind of build things and kind of go back and forth. So let's get into that right now. All right. So first thing is here. Let's refresh our memory on Ohm's law, and if we recall Ohm's law, and I don't know, maybe we should pick a different color. What do you guys think? This color? Brighter color? Okay, so we've got Ohm's law, and it states that voltage equals current times resistance, which also means that current equals voltage divided by resistance, and it also means that resistance equals voltage divided by current. And then we also learned how to compute power, which is not part of Ohm's law, but we're going to put it here anyway. Power equals voltage times current. And then here's something interesting. Because of Ohm's law, we have, say, voltage and we have current here. We can write power in terms of voltage and resistance and remove current. So voltage equals current times resistance. So that's one thing. Current equals voltage divided by resistance. So if we replace the voltage here with if we replace current here with V over R, then we're going to get V times V over R, which of course equals V squared over R. Now this is really important. So power equals V squared over R. And this is important because it shows us that the power dissipation in a resistive circuit is proportional not to the voltage, but to the voltage squared. And that's why voltage is so important in systems, in computing systems, to lower the voltage down. So we've went from, in the 70s, from 12-volt systems, now we down to 5-volt systems in the 80s and 90s. Now we're down to 3-volt, 3.3-volt systems. We're down to 1.8-volt systems, 1.5-volt systems, and down to 1.2-volt systems even. And we keep trying to decrease that V so that this term right here decreases because it goes up as a square of the voltage. So keep that in mind. All right, so we have all of our equations over here, our modeling equations. So now let's go ahead and let's do some circuits again to kind of reinforce Ohm's law. All right, so we're getting pretty good. So I'm going to kind of go fairly fast. Let's get our calculators out and kind of follow. So let's do something. Let's say that we have a 9-volt battery. And in fact, let's not draw these as batteries. Let's draw these as just voltage sources. Okay, let's just keep things simple. So there's a voltage source. All right, and we've got a resistor. All right, and let's say this is a 9-volt battery, like we said, but we're drawing it as a voltage source. It's 9 volts. And then we've got this resistor. We'll call this R1. All right, and let's say that this equals, let's say 10K ohms. All right. So when we create this circuit right here, we've got a closed loop. We're going to get a current. We're going to get a conventional current that's going to go in this direction, always from plus to minus. That's the way that holes are going to flow, or conventional current. And now we want to compute what the current is, and let's call this I. All right. And so the first thing that is going to happen is, as we have a current which is flowing through the circuit, we're going to get a voltage drop. So in the direction of the current, so this is really important. So here's the direction of the current right here, right? The voltage over this resistor is going to drop plus to minus. All right, so there's going to be a voltage drop over the resistor, and there's going to be a current that's generated in this circuit. So the first thing is, what's the voltage drop? So if we come down and we draw ground right here, all right, so that's ground, and this is 0 volts, let's say. So at this node, remember, every conductor, all the voltages are the same in the conductor no matter where you are. All right, so we're at 0 volts here, 0 volts here, 0 volts here, 0 volts here. So we're at 0 here, and if we increase by 9 volts, we'd be 9 volts up here, right? So 9 volts up at this node, and we would be 9 volts at this node as well. And the entire voltage will have to drop over this one resistive element, so to get us back down to 0 volts. So we know that there's 9 volts that drop over that resistor, which makes sense because there's just one voltage source and one resistor. Okay, so let's do our math. So we know that V equals I times R. We want to compute I, so we know that I equals V over R. All right, and the voltage is 9 volts over R, which is 10K ohms. All right, so when we do this calculation, so everyone get your calculator out. So we're going to do 9 divided by 10x3, 10 to the third, and we get, depending on your calculator and what your calculator, what format it puts the number in. So we're getting, let's do it in milliamps, so we're getting 0.9 milliamps. All right, so we're getting 0.9 milliamps. Now, if we wanted to, we could turn that into, say, microamps, right? We could put that into microamps. If we did turn it into microamps, what would that look like? So we have 0.9 milliamps. If we want to turn this into microamps, we're going to have to move the decimal 3 times to the right. 1, 2, 3. Okay, so we would have 900 microamps. So there's 900 microamps flowing in that circuit with a 10K resistor. All right, and so there's one example right there. All right, so as we increase this resistance, the current is going to decrease, decrease, decrease. All right, so let's do another example. So let's see if we can delete all this up. And unfortunately, this tool, it does have a rectangular copy and delete, but it doesn't work exactly the way. Well, we're going to have to give it a try. Let's see if we can get this to do what we need this to do. And where did that tool go? It is right here. Let's see. We deleted the whole thing. Let's put that back. And this is a problem using these tools. Let's try lasso tool. And let's see here. I think the background is the right color. Okay, good. Okay, let's go back to our pen that we had. All right. Okay, good. Okay, so now let's do another circuit. So let's say that we have, let's do batteries this time. All right, so we're going to have one battery here, and let's put another battery here. So we've got series batteries, and let's say that this is a 1.5 volt cell. Maybe it's a AA battery, right? So we could say that's a AA battery just for fun. And we could say that this is also a 1.5 volt cell, and we could say that this is, say, a AAA battery. So here's plus, here's minus, here's plus, here's minus. So we'll figure out what's going on there in a second. And now, and again, these are the symbols for resistors. We've seen this before, but we're going to really formalize this in the lecture in a little bit. Okay, so we have two resistors. So now R1 and R2, and again, you know, this course, we're not going to do an enormous amount of circuit analysis. We're going to do a little bit of circuit analysis. We want to learn all these things and how to do them. And one of the most important things when you're trying to learn circuit analysis is you have to be extremely detail oriented, and it's a lot of bookkeeping really. And if you don't do your bookkeeping and draw things properly, you're just going to get confused. So we've got resistor 1, resistor 2. We've got these voltages here. So let's call this V1 and V2. All right, and again, let's put a ground here. Okay, so we've got two resistors, and let's set these. So let's see here. Let's see that we're going to put 3 volts here. So let's go ahead and put a couple of common resistors. So we'll say that this is 100 ohms here, and let's say that this is 330 ohms here. Okay. All right, and you know, my omega symbols aren't as good as they could be. Maybe you can draw them way better, but as long as you know what you're talking about, you're good. Okay. So the first thing is, let's deal with the batteries over here. So what's going to go on with these two batteries? So we've talked about this before, and since we're putting these in series, and minus the plus, the voltage will add up. So the total voltage will be 3 volts. So from here, this point here, to this point here will be a 3 volt difference, or 3 volt potential. So now we could simplify those batteries into one virtual battery or one abstract battery. That's 3 volts, but we're just going to say 3 volts instead of redrawing it. So now we've got 3 volts. We know we're going to generate a current here. So let's go ahead and let's draw the current. So let's start getting a little more colorful here. We might as well. All right, so we're going to get a current. The current's going to flow in the circuit. It's going to flow through both resistors. All right, in this direction, conventional current, right? Now, so here's some important questions, and now we're going to start getting into the nitty-gritty. We're going to start, you know, picking up the pace a little bit. And so this current here, and let's call this current, we'll call this current just I. Question: the current I that goes through R1, is it the same current that goes through R2? So I want you to think about that for a second. Think about that for 1 second while I do some drawing. All right, so what do you think? So is it the same current, or is it a different current because we have different resistors? Now, whatever you said, let's think about this at an atomic level. So what is current? Current is the actual motion of electrons, or in conventional current, it's the motion of holes. The bottom line is we've got little charges that are moving around the circuit. All right, that's the current. Okay, so these little guys are moving around here, and they're going through the wire, through the resistors, and back through the power sources, and round they go. So one charge moves in at this end, has to go through here. That same charge has to go out through here, goes down the wire. Now it enters in here. Same charge has to exit out here and go on its merry way. So now, considering that, what's your answer, do you think? It's the same. The current is the same. So the current I that goes through R1 is the exact same current that goes through R2, and you can just look at that little analogy to kind of figure that out. All right. Okay, so now let's erase some of that. And okay, and